thank you, first of all, to the festival for inviting me. Thank you to Nick for facilitating it, and everybody who's been really great and helpful. And I've been enjoying myself a lot. So I warn you that I just learned this system within the past hour, and I use the term learned loosely. So you're going to see, I'm sure, some technical glitches. I was once giving a talk at a library in New York, and I had to dim the lights or something, and they were next to me, but it was really complicated, and I couldn't figure it out fast enough. My wife was in the audience, and she told me afterwards that the woman sitting in front of her said, and he calls himself a scientist. I don't actually call myself a scientist because I'm not. What I do is I try to learn about science and then turn it into the kind of writing that I would have understood before I started writing.
It's a little hard to hear you.
Okay. All right. If you're going to be difficult, okay. I know him. Okay, so this talk is going to be in two parts. The first is going to be a more or less scientific discussion of gravity. But the second is going to be a discussion that interests me just as much, which is how we think about gravity and how it affects our lives in ways that might surprise you. What is gravity? Volunteers? Anybody want to say what gravity? Yes?
Gravity keeps us held down instead of blowing up into space.
Okay, fair enough. Good. Anybody else? Yeah? Go ahead. Either one.
Gravity is one of the four fundamental forces in the universe that makes two objects attract each other, and it's like stronger if one of the objects is like more heavier.
Right. Okay, good. Good. Yeah?
Gravity is an attractive force between matter and dark matter particles that is dependent on mass, time, and location.
Okay, good. Thank you. So that was kind of a trick question, as you'll see. And I should have maybe warned you in advance. But those are completely reasonable answers, and that's what I thought when I went into writing this book. But the scientific answer, what is gravity? We don't know. No, really, we don't know. Say that to the average person, is, not that you're average, but you know what I mean. And the answer you'll likely get is some version of, what are you talking about? But if you ask a scientist, the people will generally say, what are you talking about? Gravity is, here comes the technical challenge. Gravity is the force of attraction that makes things fall straight down. But if you say the same thing to a physicist, what is gravity? And you say, I don't know, the physicist will say, that's right, we don't know. Now, I know that that's the answer because that's what I got every time I asked a scientist. And the idea is that we don't know what gravity is, and just about nobody knows that we don't know what gravity is, and the exception is scientists. And they know that we don't know what gravity is because they know that they don't know what gravity is. The assumption that they do, that we all do, is understandable. Unless you think hard about gravity, your brain does what it evolved to do, associate gravity with your relationship to the ground beneath your feet. You don't have to think about gravity because you know it in your bones. But if you do think about it, you can begin to realize that what you know is, in fact, a series of illusions. So let's break this sentence down piece by piece. Gravity is the force of attraction that makes things fall straight down. Well, yes, depending on what we mean by force. We can say that gravitation is one of the four fundamental forces, but it's such an outlier that the word force becomes nearly meaningless. Does anybody know what the other forces are? The other three forces? Yes?
Electromagnetic force is the strong and weak nuclear force.
Excellent. So the strong nuclear force, which keeps atomic nuclei together, is about 100 times stronger than the electromagnetic force, which creates the light spectrum, which in turn is up to 10,000 times stronger than the weak nuclear force, which facilitates the subatomic interactions responsible for radioactive decay. Three forces, all within 6 orders of magnitude of one another. Then comes gravitation. It's about a million, billion, billion, billion times weaker than the weak nuclear. To put that discrepancy into perspective, we're going to perform an experiment. It's one that you can perform at home too and amaze your friends and family. Could I have a volunteer to come up? Fine, great, yeah. Hi, what's your name?
My name is Haraz.
Hi, Russ. So, what I would like you to do here is, get my notes here. Okay, I'm going to put this here. Paper clip,
right.
Normal paper clip, right?
All right.
Do you want to put it down? You can.
Sure, I'll put it down.
Okay. Okay, so now it's held by its gravitational force to the Earth, right? And it can't move. Now the Earth's mass is more than 6 sextillion tons. That's a 6 with 21 zeros after it.
It's a lot.
It's a lot. Okay? A paperclip's mass is 4/100th of an ounce. That's a 4 with 1 zero in front of it. Now, what I'd like you to do is to take this magnet, and you can examine it. It's an ordinary refrigerator magnet, and wand it over the paper clip. Well, maybe not one, just place it there. There you go. Good. There you go. You have defeated the force of gravity, the so-called force of gravity. You have beaten the Earth.
I did it.
You did it. Thank you. And you can take that with you.
Oh, I appreciate it.
Yeah. Well, I'll need that one. Thank you. Okay, so gravitation is unmistakably weird just in terms of its relationship to the three other forces. But even weirder to physicists is that gravitation is the only force that doesn't have a quantum solution, meaning a theory that explains the force in terms of subatomic particles. The strong nuclear has quantum chromodynamics. Electromagnetism has quantum electrodynamics. The weak nuclear has quantum flavor dynamics, and gravitation has nothing. The discovery of the graviton would help. It's a hypothetical particle that would work with nature on gravity's behalf in the same way that the gluon does for the strong nuclear, or the photon does for electromagnetism, and the W and Z bosons do for the weak nuclear. But if the graviton exists, it has escaped detection with a cunning unparalleled in quantum experiments. So let's strike force from our sentence. Whoops, I just dropped that. And it turned off. I promised you technical glitches. I will just have to project even more. Unless, is it up there?
Go ahead and start. So.
Okay. Okay, so we had this. Gravitation is the force of attraction that makes things fall straight down. And now we're saying we're going to take away this. Thank you. So, gravity is the attraction that makes things fall straight down. Well, yes, depending on what we mean by attraction. Two bodies of mass don't actually exert some mysterious tugging on each other. Newton himself tried to avoid the word attraction for this very reason. He famously said he feigns no hypotheses. He has no suggestions as to what gravity is. All he did was find the math to describe the motions both down here on Earth and up there among the planets, of which at that point Earth was now one. Still, he was as powerless as a paperclip once the idea of attraction at a distance, quote unquote, entered the common vocabulary. So, gravity is what makes things fall straight down. Well, yes, depending on what we mean by straight down. The path only seems straight because you're standing still relative to the Earth. As Galileo realized in the 1630s, well, let's use his own example, actually. Let's say there's a ship on the water. There's someone at the top of the crow's nest, and there's us on the shore, and the ship is moving. Let's say it's moving from our point of view left to right. And let's say that the sailor at the top of the mast drops a rock. From their perspective, the rock will indeed fall straight down and land at the base of the mast. And I have to adjust this, sorry. Oh, right, I have it here. Oh, shit.
This is sometimes known as
No,
Galilean.
it's supposed to be, okay. So I told you, and you didn't believe me. Okay. Okay, I'll try again. I don't know how to get that. Oh, I see. Okay. Okay.
It's supposed to be muted.
Yeah. Okay. So we see it, the ball falling, the rock falling, and it falls. Yeah. I'm a Mac guy, so I don't know what.
Just don't touch this wheel here. Just don't touch it. Just
Yeah. Okay. Okay, so there goes the rock. Falls straight down from the sailor's point of view. Now, see, I can't. I didn't touch it.
There's like a button on the side here as well, but sorry.
See? Anyway, here's the idea, okay? So the rock falls straight, just let it play through, it's fine. Okay, so we're going to see the rock fall straight down again, and that's from the sailor's point of view. Okay? That's not our point of view. Our point of view is this: the ship is moving. Okay? He lets go of the rock, and it falls on a curve. So from our point of view, it's not falling straight down. It's falling on a curve. Now, who is right? Galileo's great insight is that nobody's right. Neither of us is right. Or we're both right, depending on which way you want to say it. But you can't say definitively that the rock is falling straight down. But let's say instead of standing on the shore, we're standing somewhere other than Earth. And Earth is, of course, rotating on its axis. So that's another motion that you have to factor into it. Not just that the ship is moving and we're standing still, supposedly standing still, but that the Earth is also rotating on its axis. And of course, the Earth is also orbiting around the sun. So that's another motion that you have to take into account. Now, that's if we're standing off of Earth, right? And of course, the planet, our planet, is just one more in the solar system. And the solar system is orbiting the center of the galaxy. So the solar system is also in motion. So there's the sun in the center, and here are the planets going around it, including the Earth. And so this is what it looks like if you're not only standing outside of Earth, but standing outside of the solar system, or standing outside of the galaxy, I should say. This is the motion that the Earth is going through. And our galaxy, which I won't show, is moving toward other galaxies and vice versa. And the universe is expanding, and expansion is speeding up, as Nick will be able to tell you. And while Einstein didn't know that about the expanding universe, let alone the acceleration of the expansion, he got the general idea. Your position in space, your perception of space is relative. And he's made this clear in 2 quotes. The 2 eruptions of Mount Vesuvius occur at different times, but at the same place, that is, at the crater of Mount Vesuvius. The lighting up, indeed, the Earth rotates about its axis, this is what we were just discussing, moves around the sun, and furthermore moves together with the sun toward the constellation of Hercules. Therefore, one cannot seriously claim that the 2 eruptions of Mount Vesuvius occurred at the same location in the universe. From this example, it is seen easily that no sense can be attributed to such statements about equilocality, or the same place. We can only say the 2 eruptions of Mount Vesuvius occur at the same place relative to the Earth, not relative to anywhere else, no matter where else you are in the universe, unless you're co-traveling with the Earth on that extremely weird loop-the-loop, and all the other motions associated with it. Okay. So let's make one more adjustment to our key sentence. Gravity is what makes things fall. So we got rid of straight down. But again, well, yes, depending on what we mean by fall. We can just as easily argue, as Einstein did, that the rock isn't falling toward the Earth, but that the Earth is rising toward the rock. It certainly might look that way to someone observing from anywhere else in the universe. So, gravity is. Well, yes, depending on what we mean by is. We know what gravity does in the sense that we can mathematically measure and predict its effects. What happens when 2 black holes collide or we let go of a rock. But we don't know how it does what it does. We know what its effects are, and we can give the name gravity to the cause of those effects, but we don't know the cause of that cause. Not that cosmologists particularly care, and you can correct me if I'm wrong. In science, knowing what you don't know is a good start. In this case, knowing what they don't know has led scientists to believe that finding a quantum solution to gravity is a key, perhaps the key, to understanding the universe on the most fundamental level. Until then, they will work with what they do know, no matter what everyone in their bodies tells them. Gravity is not the force of attraction that makes things fall straight down. Okay, there's the end of the strictly science part of this talk. But we, of course, don't experience gravity in the way that I'm just describing. I don't, even though I know what I know, which is what I just told you. But this is not how we think about gravity. We think about gravity without thinking about it. It's like when we say the sun is going down. We know the sun is not going down. We know the Earth is merely turning on its axis so that from our position, the sun is disappearing from view. But what do we say? We say sunrise. We say sunset. And no, don't worry, I'm not going to break into a song from Fiddler on the Roof. But even though we say sunrise, sunset, we know better, quote, know better. Can I have another volunteer? Yes, please, come up. What is your name?
Avik.
Avik, very good. Now would you stand over there, please, and stand on 1 foot. Face the audience, please, and stand on 1 foot. You can put out your arms if you need to. Keep your balance. That's very impressive. This is amazing, I have to say. If Texas A&M has a sports department dedicated to standing on one leg, you've got a scholarship in your future. Oh, for God's sake, fall already. I'm going to go back to choosing you. Thank God we booked this auditorium for 3 hours. Yeah. Well done, though. Here. Thank you. Thanks. That was great. That was very impressive. Okay. So what you were doing for a while, for an reasonably long while, was keeping in balance. But eventually, whatever gravity is, overcame you. And you can think of that as the universe. Like the universe is so tightly balanced that if the value for gravitation were any different at all, the universe would collapse or just expand rapidly. It wouldn't exist anyway. So that's how finely calibrated it is. But it's also a demonstration of what we do when we walk. And scientists actually call walking a controlled fall, because we move forward, we fall, and then we catch ourselves. And then we resist gravity for a while, we lift up, and then we fall again and we catch ourselves. And so this is how ingrained it is in the way we relate to the world, right? I mean, this is what we learn to do. It's a major achievement in childhood when you can first get up on your arms, and then when you can crawl, and then when you can stand up eventually. Okay, so this part of our existence is, I think, so basic that we don't think about it, but we invoke it, we live it constantly throughout our existence. I'll use one example here, I could use many, but I'll use one example here, how gravity affects our culture in ways that, our culture, by our culture, I mean the arts, and especially characters in the arts. So characters in the arts relate to gravity in 3 ways. They deny its existence, they defeat its influence, they defy its impact. Deny, defeat, defy. So let's start with deny. How do you possibly deny that gravity exists? Well, you can do so if you don't exist, by which I mean if you're not a real character. Consider Wile E. Coyote, perpetual nemesis of the Roadrunner, perpetual loser in the battle of wits, and perpetual faller off of cliffs. Oh, I'm sorry, I skipped something. Go back to that? Okay, I'll go back to that. So the horizon, because we're naturally associating ourselves with the Earth, the horizon is down there, is across there, and the Earth is down there because we associate it with us, and the sky is up there. And actually in creation myths, I was doing some research, and virtually all, if not all, creation myths begin with the idea of sky and Earth. That's how basic it is to our existence. And then after a while, it continues to permeate our existence, and we assign up there, which is mysterious, the name of heaven, and down here, which isn't mysterious, well, it is, but the idea of hell below us, right? And that's all horizon defined. And you can see it here in culture, the Last Judgment, on the ceiling of the Sistine Chapel. You see You can see down here the landscape of hell, and up here, the landscape of heaven. Okay, now I said about Wile E. Coyote. So there he is falling off a cliff, and he says, bye, right? But who believes it? Who thinks he won't live to suffer another humiliation at the ingenuity of the Roadrunner? Even when we witness the result of this impact with the Earth, a coyote-shaped crater, we know he'll be back immediately in the next scene. So the denial of gravity is part of the joke, right? It's the crucial part. Now, here's one of my favorite examples of cartoon characters denying the existence of gravity. It's another Looney Tunes clip, and I don't know, the mind meld at the Warner Brothers studio 70 or 80 years ago tapped into some eternal truths.
Flowers. Rest in peace, poor little bunny.
This may be the longest fall in the history of the movies.
Oh, you darling.
And he's denying gravity.
Did you see what nearly happened to me? Ooh, yeah, I gotta be more careful.
Too bad. But the joint had it coming to him. He should have watched the step.
Nah, not really. If Bugs Bunny had died, that would have fooled us. But we knew he wasn't going to. Another example of the same idea of denying gravity, which I'll show in a moment, is so similar to this clip that I have to think that it was kind of an homage to it, an imitation of it. And again, it's a long fall. And this time, the characters are actually human. They're not animated, but they may as well be animated. They're cartoon characters. And that's, and I apologize in advance for the quality of the clip. I couldn't find a clip that would allow me to plant it into a PowerPoint. So what I had to do instead was find a clip on YouTube of somebody who had filmed the scene off their television. So you're getting 2 generations removed, but we'll do our best. And this is Pee Wee Herman. So characters who aren't real get to deny the influence of gravity. Characters who are real, however, have to defeat gravity or not, at least if they are to survive in the universe we all inhabit. Do you know the films of Alfred Hitchcock? People, you do? Okay, good. I'm not sure if they translate to the younger generation. But I'm going to use some examples. In any case, I grew up with his movies. And as I was writing the book and as I was thinking about gravity and how we see it in popular culture, I kept thinking of his examples from his movies. And I realized that he uses the idea of defeating gravity as if it were a moral code. I'm not saying he thought of it as a moral code, very possibly he didn't, because that's just how ingrained gravity is in our relationship with the universe. So let's look at some examples. Sorry. Okay, so this is from the film Saboteur. The villain is trying to cling to the Statue of Liberty. He's hanging by a thread, literally, as you'll see in a moment. And because he's the villain, what do we expect is going to happen? Right. He's going to fall. There's going to be some sound in the first couple of seconds. This is taken from an interview with that actor, and so you're going to hear the transition into the scene itself. Oops, sorry. Sorry.
But for a fugitive on the run,
Oh no, I'm sorry, this is from the trailer.
last chance he has to clear himself. And it could end his life. Can you get a grip on your feet?
I can't.
That was from the trailer, and they showed the climax of the movie. It's like a trailer for one of the Star Wars movies where it goes, "Luke, I am your father," you know. It's like, oh, okay. Okay, so no surprise there. The villain is no match for gravity. The villain can't defeat gravity. The hero, though, the hero's very identity as a hero depends on the ability to defeat gravity. So this is from another Hitchcock film called North by Northwest, and it's from the climax. You'll notice that the hero here is in the same position as the villain we just saw. We know that the villain in Saboteur couldn't, of course, defeat gravity. Can the heroes in North by Northwest? Let's find out. No. Thank you. Okay. There it is. The villain.
Thank you, Sergeant. That wasn't very sporting, using real bullets. Here, reach. Now. Come on, I've got you. Up.
I can't make it.
Yes, you can. Come on. Come along, Mrs. Thornhill.
Oh, Raj, this is silly.
I know, but I'm sentimental.
Okay, we lost the syncing there for a second. But, so, thank you. So, So ingrained in this are we that we know the Hitchcock, we know the climax so well. We know who's going to survive and who's going to die. And we know it so well that he doesn't even bother to show us her being pulled up. Instead, he cuts to the train where they've been married and now they're on their honeymoon. So we know that, of course, they're going to defeat gravity. So with Hitchcock, the villains fall and the heroes rise. That's simple enough. But I found that when the morality in Hitchcock movies becomes murkier, so does the outcome. This is from Rear Window. That's the actor James Stewart. He's broken a leg, so he's confined to a wheelchair. And in order to pass the time, he begins spying on his neighbors in the courtyard out the window there. And so he's looking into all of their windows. Now, in the end, he solves a murder by doing that, but he solves a murder by spying on his neighbors, which isn't very nice. He's being a voyeur. And here he is in that familiar position, the same one we saw in Saboteur and North by Northwest. In this case, yes, he's the hero, but he's also kind of a villain in his own way in that he was spying on people. So his fate This is glitching, sorry. Well, anyway, thanks, Nick. I'm just going to go on because the last one was unsynced and this one just isn't moving. So suffice to say that he falls, but he breaks his other leg. So that is his punishment. So he still gets to defeat gravity, but he still gets his comeuppance. And here's the end of Vertigo, another Hitchcock movie, James Stewart again. And in this case, our hero suffers from vertigo, a fear of heights, but he also is way morally compromised, much more than in Rear Window, what we just saw. He's obsessed with the mysterious woman. He wants to possess her. He's sick, and not just with vertigo. And in the end, his obsession leads to her accidental death. You can see here that the accident has cured him of his vertigo, right? Can you dim it just for a second? He's on a bell tower, and you can see he's on a ledge, high off the ground, and suffering from vertigo. He shouldn't be able to do that, but he's just witnessed her death, just accidentally caused her death, and therefore he has to, he won't fall because he's the hero, but he is actually going to suffer a fate worse than death, in that he's going to have to live with himself. So you can see how complicated the morality can become. Nick? Thank you. Finally, we come to defying gravity. And if I can't get the videos to work, it's not going to make any sense. Now, okay. Laurel and Hardy.
Pardon me, Mr. Postman. Yes, sir. Could you tell me where 1127 Walnut Avenue is? 1127 Walnut Avenue? Yes, sir. That's the house up there, right on top of the stoop. That's the house up there, right on. That's the house up there, right on top of the stoop.
It's unsynced again, sorry. Okay.
Steady, Sue.
So they're going to have to defy gravity. Okay. So let's see them do it. Okay, so far so good. But then, sorry, that's another glitch. Suffice to say that the piano falls down the stairs. So then they are going to have to try again, because what else do you do? Okay, so it's a riff on Sisyphus, right? They're going to just keep rolling the ball up the hill. Their persistence is noble, I think. They're going to keep doing it because what else are they going to do? Give up? As I think back on the idea of dropping a rock or falling downstairs, it begins to take on a different meaning for me, eventually when I was writing the book. It's not a meaning I can always grasp, even today. It's not an idea I walk around with all the time, but I find it fun and moving and mysterious. And I hope that if you think back on this talk, you might also find gravity to be fun and moving and mysterious, which brings us back to right where we started. Thank you.
Thank you, Richard. There are some students here who are in astronomy classes, and if you're in astronomy class, there's a sign-up sheet with Kevin Christianis, the guy that looks like Steve Martin back there. So put your name and class number on it. We have time for a few questions, so please
Since people are leaving, can you tell them that the book will be for sale?
Oh yeah. Well, one other thing too is the book is going to be for sale after here. You can get a signed copy of Richard's latest book.
Thank you. Thanks.
Questions? Is there a question behind?
Yeah. So you were saying that we don't have a particle in gravity yet, but
Go ahead.
should I wait until we're less talking?
If I can hear you, and I'll repeat the question, okay?
Okay. So from what I have learned, is gravity just like the deformation in space-time? Like if you have space as just a flat plane, wherever there's a lot of mass, that plane gets deformed and sucked downwards. So any given object would, from its own perspective, always be moving in a straight line. But because the plane that's moving on is deformed by gravity, from an outside perspective, it would be moving in a curve. So is it possible that gravity isn't any kind of force at all, and it's just how we describe the fact that that plane is being deformed?
Okay, the question is that there's still no quantum mechanical particle that has been discovered for gravity.
Right.
So
I'm saying there might not need to be one.
Yeah. So
it might not be a force like we think of the others. It might just be how we describe that deformation.
So if gravity is described by deformation of space and time, is it really a force?
Exactly.
Okay.
Do you want to handle that? It's more your.
No. It's a very profound question, and it kind of goes back to Isaac Newton, who was troubled over what force actually meant. And although Isaac Newton is famous for his 3 laws and the law of gravity, the subject he spent the most time on was trying to figure out what force meant. So in an everyday sense, gravity really is a force. It's like all the other forces. But in a mathematical sense, as Einstein showed in general relativity, you can describe gravity as a curvature in space and time. And so in that sense, some physicists like to say that it isn't a force, but it is the nature of space and time that sets the rest of the universe, the rest of the forces in the universe for us to study. And gravity itself is a more fundamental concept. And the other ones emerge, all the other forces emerge out of curved space and time at a quantum level. So it is in modern physics thought about sometimes not as a force, but as something else. It's a big, interesting, controversial subject, and there are a lot of people working on it and a lot of people arguing back and forth. And there's no answer at this point, but intellectually it's a very interesting thing to pursue.
So it's one of those things that may not strictly be a force, but it's generally most useful to think of it as one.
Yes. The paradox being that at the microscopic level, when you look at the laws of quantum mechanics, the arrow of time goes in both directions. So as a particle goes forward in time, is mathematically identical to a antiparticle going backwards in time. So it has perfect symmetry down at the microscopic level. But at our macroscopic level, our arrow of time goes in one direction. So there's some place in the mesoscopic level between those two where something very special happens, where time, which is reversible at the subatomic level, that becomes unreversible. And physicists are looking into the kind of quantum, the foam nature of curved space-time as the thing that changes from the subatomic level up to the macroscopic level. And so gravity becomes not just a force, but it becomes part of the definition of time. Yeah.
Richard, what was your motivation for writing this book?
What was your motivation for writing a book, Richard?
Thanks. The idea came to me one day, that's all. I thought, what is gravity? And then I started looking into it, and the book opens with me falling over in a bookstore, actually. And actually, I had just been reading, I was killing time in a bookstore. I pulled a book at random off the shelf in the science section, opened it to a random page, and it was talking about gravity. And it was talking about the mysteries of gravity. And I thought, oh, is gravity just a useful fiction? And then, I sat there for like 15 or 20 minutes, and then I closed the book and I stood up, except I didn't really stand up because my foot had fallen asleep. So I fell down. And that got me also thinking about it. The fact that it's a useful fiction that we are all subject to nonetheless. Thank you, that was a good question. Yeah. Yep. That's a great question. The question was, is it just Western cultures where see gravity in a negative way? But it's, yeah, that sees gravity in a negative way because the villain falls down. Sorry? Or did you find contrasting examples of anything? I didn't find contrasting examples in other cultures, but I did find that consistency in the culture, the creation myths, that it was always assigned in that fashion, positive and negative, and that we were expelled in some way, or we upset the gods and were relegated down here, which is, the Garden of Eden, right? But it's culture-wide, and in fact, once I was doing research on creation myths, and I came across a quote from, I guess, the preeminent scholar of creation myths in the mid-20th century, and he called basically up there and down here, sky and earth, the primeval pair.
Any other questions?
Okay, this might be a stupid question.
No.
Questions are stupid.
Okay, so we can agree that gravity has an effect everywhere in outer space, right? But once we get to outer space, there is zero gravity. Oh,
No.
No?
No, everything in the universe is, thank you. The question is, once you get to outer space, isn't there zero gravity? And again, Nick, please jump in whenever you want, because you're the expert. As I said, I'm no scientist. My understanding is that everything in the universe is gravitationally attracted, and I use the terms loosely, to everything else. So that if you had an atom of hydrogen and then 13 billion years, light years away, you had another atom of hydrogen. They would be in gravitational contact, and nothing else in the universe. They would still be in gravitational contact with each other. Is that right? Yeah. Okay. Yeah.
Just isn't it in outer space that the force is so small to the great distance that you don't notice it, or it's so difficult to measure due to how small that force is?
I think that that's right. Would you?
Yes and no.
Okay. Yeah.
Yes and no. What really is the case is that the force of gravity doesn't change very much from one point to another in outer space. But there's a huge amount of gravity out there. It's the gravity of the whole universe. And the whole universe is causing curvature. And so space and time are curved and affected you are affected by gravity everywhere in the universe. All of the atoms and everything in the universe is producing a gravity at your point. But if you move over here, there's very little change in the gravity that the universe is affecting you. So you don't notice that. It's like gravity is. But you do notice gravity changing if you're very near a black hole. So there is lots of gravity out there, but it's all at the same level. You have to go great distances to see changes in gravity when you go across the universe.
One more, I guess, if anybody wants one. Yes?
When you were introduced, I didn't hear a whole lot of technical background. I heard a fine arts school and a writing background.
That's right. Yes.
How did you do this?
An editor approached me, an editor who liked my nonfiction writing approached me in the mid-1990s about doing a history of the telescope. And I said, that sounded deadly. I took a lot of AP courses in high school to get out of science in college. But she said, oh, think of it as an essay. So I did some, and think of it as a shortish essay, like 200 book pages or so. And she said, take a month. So I took a month and looked into it, and I thought, oh, what's really interesting here to me is not the technology, but the history and the philosophy and how it affects the way we think and how we see our place in the universe. And then one thing led to another. And then one day I was daydreaming in a grand jury, which you get to do a lot of because there's a lot of downtime in a grand jury between calling witnesses and stuff. And I came up with the idea for my next book. I saw a parallel between Einstein and Freud. And in doing that book, I started to learn about dark matter and dark energy. And I thought, okay, Einstein and Freud are dealing with the invisible. And here's something that is not just invisible, but undetectable on any level. And then gravity just kind of, probably came out of that interest that not just only undetectable, but debatable. Thank you. Good question. Okay.
Let's thank Richard for a wonderful talk.
Well, thank you.
I am here today at the Physics and Engineering Festival. I'm your host, Morgan Nasser, and I'll be walking you around, showing you some demos and talking about science. Could you tell us what we have here?
So what we have here is an aluminum cylinder that's airtight, and I put liquid nitrogen in it.
Okay.
So what liquid nitrogen is, more or less, is it's air that gets so cold that it turns into a liquid. But it's still the same nitrogen that's in the air all around us. But when it heats up, especially on a hot day like today, then the liquid nitrogen wants to turn back into a gas. And when it turns back into a gas, it gets more than 700 times bigger.
700?
700 times bigger, yes. So as I put the nitrogen in here, I jam it with a cork so that there's nowhere for the excess gas to go. And as it turns into a gas, it gets bigger and bigger, but there's nowhere for it to go. So the pressure builds up and builds up and builds up until the cork can't handle it anymore and it pops way up into the sky.
I see. That must be how these big barrels work.
Yes.
All right. Well, safety first, so if you're going to fire that off, I'll cover my eyes.
So I fill this aluminum cylinder with a little bit of liquid nitrogen, and then it expands and expands, and then I jam the cork in here, so that the pressure can build up, and boom! It goes way high into the sky. And this is the same nitrogen that's in the air all around us, but because it's so cold, the physics of it completely changes.
Wow.
And it can do this crazy stuff like this.
That's amazing. I can't wait till those go off. Do you remember how often these do?
It happens every 30 minutes. I believe
Every
it's
30
on the
minutes.
30-minute hour, 30-minute hour.
I see. Well, let's see. We definitely have to see that one. We'll probably see the finale at 3 as well. It is about 20 minutes from there. So let's go see some other ones. Thank you so much.
Of course.
This one's really cool. So, well, I'll have them explain it. Basically, long story short, they drop everything and the ball on top goes, whoa. Hey, how's it going?
Howdy.
I thought I'd ask you some questions over what this thing is. It looks like one of those old toys that, you stack or whatever.
Oh, absolutely. So this is called the Galileo Cannon, and basically it teaches conservation of energy and conservation of momentum. So as the energy travels through each respective ball, first from the table, then to each incrementally smaller mass, the energy gets more and more refined until it has nowhere else to go eventually. So let's see what happens when we release this. Yes, so as you can see, once the energy got from the table through each mass to the top, the energy had nowhere else to go but up, and eventually it even doubled its height as it got to the top.
Oh wow, yeah, that was pretty impressive. You only dropped it from about here, it went like 2 or 3 times higher.
Exactly.
Very cool. Well, thank you so much.
Absolutely.
All right, on to our next one. Can you tell us about this this tub?
This tub of water mixed with cornstarch.
Okay.
This is our cornstarch pool. It's a pool of water mixed with cornstarch that you can walk on top of. Thing about it, non-Newtonian fluids, if you hit them really fast, they act like a solid, but if you sort of ease into them, they act like liquid, so you can sink into it. Some of these kids like to stand there and sink, get themselves stuck, and some of them will run across it. You can see some kids like to just sit there and get stuck.
Oh, wow. So yeah, he's kind of just sinking there.
Yeah. Yep.
So when it's slow, it's like a liquid. When you're moving fast, it's like a solid.
Like a solid, yeah. Sometimes we try to tell them that if they're stuck like that, they have to stay here and be physics majors. But,
Good job. I didn't like that.
No?
Never doing that again.
You've done it like 5 times.
Seems like he liked it. Thank you so much. All right, and over here we have some catapults. I had to make our way down here to see these. Nothing's cooler than things flying. Howdy. We were curious why there were things flying around. Could you tell us about some of this stuff?
Yeah, sure. I mean, more or less. So these two on the ends, all they do is they just convert gravitational potential energy into kinetic energy, right?
Okay.
So all you do is you lift up the weight, right? And then whenever you let this pin go, the weight falls, right? And then whatever energy difference there is from the top to where it falls to is going to be the more or less the energy that the ball has, right? And so that's just the basic operating principle of these, right? So these are medieval siege engines. And so they would actually use these in medieval times to fling large boulders, at castles and towns and all those sorts of things.
Cows?
Towns.
Oh, okay.
Yeah. No.
Did they ever fling cows?
So they actually did used to fling dead bodies in trebuchets, right, to spread disease, interestingly enough. Yeah, they had some very odd techniques in medieval warfare, right? So
it does sound very odd. A different time.
Yeah, actually, yeah. So they would spread the plague that way to their enemies to weaken them, right? So they could easily conquer them, right? So anyway, but yeah, well, obviously we're not doing that here. So
No, of course. This is the modern time.
Yeah, exactly. Yeah, we do it different ways now. So
Now,
yeah.
this one is, I think this one's called a trebuchet, right?
Yes, that's
Is this
correct.
one? What about that one? I've never seen that before.
So the one
far
at the end, yeah,
Yeah.
that's also a trebuchet as well. It's just a more perhaps advanced version of it, right?
That one's more advanced than this?
Yes, yeah, that one actually, if you watch it, whenever I think they're about to let it go here in a moment, right? It goes much further than this one does. And the one in the middle is called the ballista.
The middle is a ballista.
Yeah, which works by a different operating principle, right? It doesn't use gravitational potential energy. It stores energy in the bending of the strings, basically, right? And like elastic energy. So
It kind of looks like a crossbow. Is that where that was inherited from?
Yeah, more or less. I mean, actual crossbows are more dangerous than this, of course, right? But nonetheless, yeah. So it's more or less the same principle. So yeah.
All right. Could we potentially see you fire off this guy?
Sure. Well, actually, I mean, just for TV, right? You should probably fire that one off, in my opinion. Yeah.
The one on the end?
Yeah. It's much more impressive.
All right, let's go see the one on the end.
It makes for better TV. So.
Okay.
So that's our trigger mechanism. And so I'm going to ask that one of you hold this and stand back a little bit.
Do not pull it, all right? No one's gonna pull it. I'm gonna trust you because I don't wanna lose a finger. So, I'm gonna wind it up. Go ahead and come a little bit closer. Don't wanna have that very tight. All right, don't pull it. Don't. I see you pulling it. All right, good. Okay, I'm gonna load up the projectile. And now whenever you're ready, go ahead and give that a yank.
Ready?
Go for it.
1, 2, 3, go.
Whoa! No!
Wow.
The best launch. We can do another one though.
Hey, how's it going?
Howdy.
So we just got the down low on how all of these work and what they are, and we were recommended to see this one fire off.
For sure. This is the most powerful trebuchet of all of them. So we're just about to do a demo. You might want to watch out here because this thing flies back. But yeah, we just need to put a ball in it.
How far have you seen this one fire off?
Oh, I mean, this one will hit that building over there before it touches the ground.
Really?
Yeah. It's honestly kind of hard to track with your eyes, so make sure you're looking at the start and you're looking up high.
Okay.
All right.
For now, check out that triple stick.
Make sure to stick to the side though.
Yeah. We have had a few misfires where it goes backwards.
Whoa. I think it got the truck.
No, John's there to protect it. We're good.
Well, that was so cool.
Thank you very much. It's a great pleasure to be here and to see such a great crowd. So what I'm going to do, especially since we have so many young people here, is to also trace my steps into engineering because I was not born an astronaut, right? You become one. You become an engineer. So when I'm asked, well, what is my profession? My profession first is I'm an engineer. And that qualified me to apply and become an astronaut. And then that experience allowed me to bring that to a university environment, which has been extremely rewarding for me. I'm also going to talk briefly about the 5 space shuttle flights that I've had. You know, it's hard to go in just an hour to do what they call a deep dive, really deep. But there's so much on the internet now that as long as you know what those flights were, you can actually call up the YouTubes for our crew debriefings, we call them, maybe a 20-minute video from the whole crew that you can learn, from which you can learn about what we did and why it was important. But then I'm also going to talk about what we're doing now in space exploration, because you don't always see it in the front page of the paper, and it's pretty exciting, and what the future is going to look like for everyone, but also for the young people in this audience. So I like to call it thinking outside the sphere because it's my play on thinking outside the box, right? When I was a young girl, as you'll see in a minute, I didn't have city lights to surround me and to help maybe stimulate some dreams. What I had were the stars, and it was a time in the United States history when we were starting to explore space, and that was what excited me. But just as importantly was a culture of education that came over with my grandparents who immigrated to this country in the early part of the last century. Doesn't that sound so far away? But I knew my grandfather till he died when he was 93. And he left Scotland with the equivalent of a high school education, but no one in his family had ever gone to a university. And in that period of time, as a laborer, he didn't have much future in the academic string, but he had a teacher who really encouraged him, tried to get him to learn a brand new field called electricity. And so my grandfather had this great curiosity. And while he didn't have a formal higher education background, he was extremely well-read, and he loved literature, he loved poetry, especially Bobby Burns, for any of you that have a little bit of a Scottish background, especially here in Texas, there's actually quite a bit of Scots history. And he would write all his letters to me while I was at the university in prose or in poem, and he'd rhyme just like Bobby Burns, and it was always encouraging, stick with it, don't let it down. This is really a pathway to the future. And of course, he passed that down to my father, and my mother had a similar experience with her parents coming over. And none of them had, university education. It wasn't because they weren't, bright, energetic people. They didn't have the opportunities we all have now. My mother was one of 9 kids growing up on a sheep herder's homestead in northern Montana. And my father, they grew up on a homestead here in Oregon State. Now, my grandmother was also just as independent, and you can see that. Someone asked me, is that my grandfather? No, it's my grandmother. Attired in full kilt. My grandfather played the fiddle. He was very musical. Music was a part of growing up for me. If you think about it, my grandfather was born in 1887, same time that I think Robert Goddard may have been born. And he saw the automobile. He was alive when the Wright brothers flew in 1903, but he never flew in an airplane. You can think about that. And unfortunately, he passed away just before my first space flight, but he was always an inspiration to me. So where did I grow up? Well, after World War II, my father was a Marine in World War II in the South Pacific. He came back to Oregon where he'd grown up. He met my mother, who was a waitress in the Condon Hotel, and it's one of those very romantic stories. They met at a dance, and they danced to the Tennessee Waltz. Some of you might know that. And that became their song. They married. They then homesteaded in 1948 in the Yakima Valley, Washington State, and that's where I grew up. My mother, who is 95, just recently sold the ranch. My father had passed away, so I feel like part of me was ripped out. That was my entire upbringing in the ranch and growing up on the ranch. This was the nearest post office, and I love driving around Texas because I find post offices like this, out in the country. This one's probably 70 years old or more. That was the area code 98938. And this was the view from our house, looking west to Mount Adams, Mount Rainier, looking north. When I was growing up, no lights. It was absolutely dark. The Rattlesnake Hills to the north, and I could see the Milky Way. A lot of young people don't know what the Milky Way is, right? Because they don't see it. It was this big stripe of stars coming up out of the hills. And so I knew that we were just part of something that was much larger than ourselves. And I wanted to know what that much larger was. Not only what it was, but why it was. What was causing it? What was out there? But at this time, I was born in 1949, there was no such thing as human spaceflight. There were telescopes. There wasn't a lot of knowledge coming back. We didn't get a TV till I was 9, believe it or not. There was no cell phones, internet, computers, but books. I loved books. And during the summer, when we couldn't, the school was a couple bus rides away, we couldn't go to the school library, but we had Bookmobile. How many of you know what Bookmobile is? Okay. Once a month, basically the library on wheels would come by all the farm families, stop, and you could check out 10 books for a month. And I checked out a lot of science fiction, H.G. Wells, Jules Verne, anything I could get my hands on. And when I was through with my chores, my brothers and I would retire to our very crude tree houses. And in summer months, that's where we'd spend, the hot afternoons is reading our books. And so that's how I invented my world, right? I didn't have pictures, other people painting pictures. I read books, and I could always put myself in the protagonist's place, whether it was exploring or discovering. It didn't matter what I looked like. It was, gee, wasn't that exciting? I wanted to go to Mars. I wanted to be like Flash Gordon and explore the universe. So as I mentioned, I was not born an astronaut. I share this as one of those early pictures. Yeah, I was a small kid. When I was a year old, my dad had a dream. His dream was Hereford cattle. He wanted a Hereford cattle ranch. He wanted peace, coming back from World War II for a lot of young men. That was, war is a horrific thing, and he wanted to be out in the country and raise his registered Herefords. And this was his favorite bull, Bolivar. And yes, that's me on there. That's when I was about a year old. And I sometimes do volunteer work for the Houston Livestock Show and Rodeo. So I'll go out to schools and I'll have teachers say, well, wasn't your mother just horrified, if you're sitting on this wild bull? And I said, not really. She took the pictures. There's not a lot out there, right? And Bolivar was pretty tame, and my dad was pretty proud. You can see that. And I point this out because my dad and mother didn't protect me from every potential risk out there. It was always calculated. They taught me. I was the oldest of 4 kids, so I had to learn how to ride a horse. We had rattlesnakes and coyotes that would be big enough to carry small kids away. So my brothers and I actually got our rifle safety licenses when we were about 8 and 9. So when we were riding fence on horseback, we have to do that to check the fence, to make sure the cattle stay in. We could still protect ourselves if we needed to. It was a little bit of a wild country in those days in eastern Washington. So this is growing up on our ranch, the Diamond Double Bar Ranch. My 2 younger brothers here. I have a younger sister, but she was like 10 years behind me. So she's not in these pictures. She, by the way, became a high school teacher. So she just retired from that. We raised our 4-H cattle, and I also showed my Appaloosa colt that my dad actually caught in Condon. It was running wild on my grandfather's ranch, and we trained it, which I have to tell you, learning how to take care of an animal and that responsibility really teaches you a lot. And being in 4-H, you have to keep track of all of the expenses. And I'd say out of the 9 years I was in 4-H, I only made a profit once. And my dad had to check my books to make sure that I had done it right. But he was pretty proud of that. So going to a small grade school, there were only 22 in my class for 8 grades in this rural area. But I was exposed to a lot of books, Flash Gordon. And when we got a TV, every Saturday morning, I got to watch Mr. Wizard. How many with Mr. Wizard experience? Yeah. He's still on YouTube. And guess what? The laws of physics and chemistry have not changed much in 200 years. So what he taught, whether it was about electromagnetism or other physical concepts with 2 young students, and this is black and white, by the way, real-time TV, with a boy and girl, it's still valid. You can do those experiments in your classroom now. But he taught for many, many years, Don Herbert. Sputnik was launched in 1957. I was 8 years old. And I'll tell you, that was worldwide excitement and concern because the Soviet Union built the rocket to get it there. Everyone was excited about the fact that there was a satellite beeping around the Earth, and that's what it did. It was beep, beep, beep. But there were 2 levels of concern. So my father, who had just, the nation had just recovered out of World War II, realized that, this Cold War and the Soviet Union could put something around our land. I'm a kid, and I'm just thinking, hey, this is exciting. There's something in space. So 2 levels, but everybody could go out and look for it. It was very shiny, not very big, and it transmitted a signal that you could capture on your radio and tune it in. And you can also hear that on the internet as well. It was kind of a beep, 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 beep. But that was basically the start the very beginning of space flight. We followed a little bit later, by the way, in the next year with a satellite put up by under President Eisenhower, and it had a voice transmission that went down to the ground, and you could listen to that as well. But things started to heat up. Yuri Gagarin was the first person launched into space by the Soviet Union. We followed not long after with Al Shepard in one of the Mercury 7. This was our first set of astronauts. In my lab here at A&M, I work on spacesuits. And if you compare what we wear now with what they had, wasn't that pretty nifty? Those that look like science fiction, those gold. But these weren't meant to do a spacewalk. These were meant to keep the astronauts safe inside the capsule in case they lost pressure. Al Shepard launched suborbital. That means he didn't go all the way around the Earth. He went up to this magic mark called 50 miles. We call that space. Made that so he qualified as an astronaut. Okay, we needed to go around the planet because that's what Yuri Gagarin did. And so that's what John Glenn did in February 1962. He went around 3 times. And by the way, he later flew when he was 77 on the space shuttle. He's a really remarkable man. He was not only the first astronaut to orbit the Earth from the United States, he eventually became a US Senator and really helped to keep our space program alive. And he didn't go up just because we thought we'd send him up just because he was 77. He actually started some research that we do with the National Institute of Health on aging. And I hate to say this, but there's a lot of things that happen to astronauts in space that mimic aging. So maybe you don't always see it, but it has to do a little bit with the cardiovascular system, for example, osteoporosis. And we're studying that because we have to develop countermeasures to continue exploring onto Mars. But so John volunteered, since he was already 77, to collect that data, and we can compare it to younger populations. Then a really exciting time was in 1962, when right here in Texas, in Houston, at Rice Stadium, President Kennedy announced that we're going to the moon. And that speech is also on YouTube. I really encourage you to read this speech or listen to it, because it still, for me, is inspiring now as it was then. He said, "This generation does not intend to founder in the backwash of the coming age of space. We mean to be a part of it. We mean to lead it. This country was conquered by those who move forward, and so will space. We choose to go to the moon in this decade and do the other things, not because they're easy, but because they are hard. The growth of our science and education will be enriched by new knowledge of our universe and our environment." During the Apollo program, the government invested billions of dollars in universities and in university labs to help grow that workforce. And I'm a beneficiary of that. It was something called the National Defense and Education Act. It was about a 5-year program, and it funded qualified high school students to study engineering and science, or education if they would come back and teach mathematics and science, to go to a university. And obviously we weren't, the cattle business was a little bit thin at that time. I was working in the fields. I've done just about every job, you know, whether it be a waitress, I ran a movie theater, I packed corn and asparagus in a packing plant that canned these types of things. That wasn't enough money to send me to university. But I studied hard. And so it was the grades that allowed me to go, and that was part of this program that was put in place. It's about education and new knowledge, and made it happen. But other things have to happen to make that, to enable that pathway. So I was attending Outlook Grade School, 8 grades. My 5th grade teacher, Mr. Miller, was also my 8th grade teacher, and he was also the principal. Every Friday afternoon, he would read a part of a book to us. It was, he'd say, well, and it was the 6th grade. Why at 6th grade? Because he wanted to ensure that we were reading, and he would always read something interesting. And he was reading from a book called The Angry Red Planet, which was made into a really horrible movie about going to Mars. But I hung on every word. You know, this was exciting. This was about a crew going to Mars. So as I graduated from the 8th grade, and many schools in Texas are like that, and used to have what was called an 8th grade common diploma, that allowed you to go to high school. And I was going to go to the high school in the next town, had to take another bus. He said, well, what do you want to become? What do you want to do? And I said, I want to build spaceships and I want to fly in them. And he said, you'll need algebra. And I said, what's that? He said, trust me. So I enrolled in algebra in the 9th grade. And I have to say that, it was not easy. Thinking in abstractions, X's and Y's and solving equations. But all of a sudden, something I realized that I could solve equations that applied to the ranch. If my dad said we were going to fence a certain number of acres and he wanted the fence posts at 20 feet apart, I could suddenly calculate how many posts that I needed. And I could impress him with those answers. And suddenly algebra became pretty real in terms of solving our everyday problems. So some problems we think we solve without thinking about them. How long does it take to go to Houston if I'm traveling 60 miles per hour, that type of thing, and how many miles? And that once that snapped into place, suddenly, I'm off to 10th grade and I'm taking geometry and then trigonometry and math analysis and chemistry and physics. And I took all the other stuff too, 2 years of Latin and English literature. I just loved school. And when you love school, you do better. And so I had the grades. So when the National Defense Education Act came around, suddenly I qualified for a combination of loan and grant to the University of Washington. And the paperwork came in, and it's a lot of paperwork. And I didn't know how to fill it out. So I went to my physics teacher, Mr. Anderson, and I said, there's a bunch of colleges here. I thought I was going to college. I'm going to the University of Washington. He says, no, you got to pick a college, right? And I said, well, what do I pick? And he said, I think you should become an engineer. Just that 5-minute conversation, check the block, and that's why I'm here. I became an engineer. So don't underestimate those 5-minute conversations, both on the part of the student, say what you want to become, to teachers and parents. And on the other side, you may have a great influence just with the advice you get. And so I went off to the University of Washington. My sophomore year, I joined the department we now call Material Science and Engineering. In those days, it was called Mining, Metallurgical, and Ceramic Engineering. I was enticed into it by Doc Muller, because he was working on the Space Shuttle Thermal Protection System, this really science fiction concept in the 1960s of a spaceship shaped like an airplane that would launch like a rocket and land like an airplane. And that sounded exciting, because we're already going to the moon. I wasn't going to be on the leading edge of that, but I could be part of something that was brand new. I also joined an organization that had a big influence on me as well. It was called Angel Flight, which was a co-ed auxiliary to Air Force ROTC. And we used to have a detachment here, and I hope we renew it. But it's a civilian complement to ROTC, and that introduced me into a national organization that taught me a lot about leadership, introduced me to some Air Force officers that provided my first introductions to real astronauts. In 1969, Neil Armstrong walked on the moon. And for those of you that remember that, that was the headline of the papers around the world. That made a significant impact. But we didn't just do it once, we did it 6 times, right? We landed 12 men on the moon. There were another 6 that orbited around the moon. There was a mission that went just around the moon, didn't land. And then Apollo 13 was the mission that had a problem and then was saved. Apollo 13 is a great movie if you have a chance to watch it. It was put into a special, I think, on PBS, and then into a Hollywood movie, which is pretty accurate. Our first look at the Earth came from those missions, color images. And we suddenly realized that, yeah, we're just this unique planet out here. Before we started discovering other exoplanets, we kind of thought, are we alone? Are we this only planet in our solar system? And here's the bird's eye view of what we look like. And just that view started a whole new group of scientific disciplines that we called Mission to Planet Earth, the beginning of remote sensors, where we could look at the weather and we could look at the oceans and oceanography and geography and geology. Before Apollo, we didn't even have communication satellites in Earth orbit. We didn't have these platforms that now help us understand what our planet's doing and the global look at it. Well, as I mentioned, this is the shuttle, and the picture that Doc showed me in 1968 that encouraged me to become a materials person to start with and to work on the thermal protection system for this vehicle. The shuttle launched to orbit about 200 miles up in about 8 minutes, and then it would orbit up to 18 days and then land in about 45 minutes. When it landed, it was a glider, and all the other vehicles that had re-entered the Earth's atmosphere were protected from the high heat of re-entry because you're slamming into the atmosphere with materials that were called ablative. They basically burned off. One-time use. I mean, you go down to Space Center Houston, look at the Apollo vehicle, and you'll see it's kind of a blackened shell. Go to the Smithsonian, you'll see the same thing. So how do we make this vehicle reusable? That outside shell that doesn't melt at 2,300 degrees Fahrenheit, which is pretty hot, or on the nose, which might be 2,700 degrees Fahrenheit. Well, we had to design it around materials, and so we picked some ceramic glass fibers that would melt at a much higher temperature and also not deform. So my work on some NASA grants for Doc on thermal protection system actually led to a job at Rockwell working on the first spaceflight vehicle, Columbia, and that was exciting. I tell you, there's nothing more exciting than flying from our office near LA, California, up to the high desert at Edwards Air Force Base and walking into a hangar and being part of the building of a brand new spaceship. So check, right? I could have stayed there. I mean, I loved it. I loved the work we were doing, the troubleshooting we were doing. I was given a lot of responsibility for a 28-year-old engineer, and it was just an exciting time. But then they started selecting astronauts for the shuttle. And I applied, and I was selected for the final 100 interviews. And this is why you see this article here. Rockwell was kind of excited for me because I think I was their first employee to make the finals. I flew down to Houston, went through the medicals and the interviews and so forth. But unfortunately, I was not selected. You know, but that doesn't deter you, right? If you really want something, you try hard enough. And I talked to a number of Apollo astronauts that had been rejected the first time, and you just keep trying. So this happens to be the class I was selected for, 1980, but in between the rejection and the selection, I was offered a job at NASA in mission control as a flight controller. So I took that job, and a couple years later, I've been on the Skylab re-entry team, we call it, started training for shuttle, applied, and then that's me right there with my class. I'm sorry it's a little fuzzy, but I tried to pull up an original black and white photo that they had in those days. They do have color, by the way. The shuttle first launched in April of 1981, April 12th. And as long story short, it flew for 30 years, 135 flights. In fact, I think the public would get so bored they wouldn't even turn the TV on. But every flight was unique. Those flights developed the science that we have on the International Space Station. Those flights repaired the Hubble Space Telescope and put new instruments on them. And those flights helped to build the International Space Station that's orbiting us right now, once every 90 minutes. How many of you have gone out and looked for the station? Good. And most of you, I hope you know you can see it over College Station or Texas, anywhere. There's an app for that, okay? It's called Spot the Station. Tell it where you are, it'll tell you when you'll be able to see it. And it's about as bright as Venus. You don't need a telescope for this. And my mother, 96 now, she does that. And she'll call me and say, look, the station's coming over tonight. And I'll have to remind her, yeah, it's coming over Washington. You know, the orbit's precessed. But she gets excited about that and calls the neighbors. So we built 5 shuttles. We flew those for quite some time. And I'm going to show you just a very short video, so I want to remind you, we call this the external tank, and this feeds fuel into the 3 main engines, and then 2 solid rocket boosters on either side. All together, with 5 engines, we get to orbit, but we drop the 2 solid rocket boosters at 2 minutes because we exhaust the fuel, and we don't need the dead weight, so we drop it and then continue the rest of the way on the main engines. It was a roomy vehicle. My first flight had 8 crew members, 8 up, 8 down. It was a joint mission with West Germany. We controlled from the flight deck, and then we lived down here. We performed experiments. We had our medical experiments. We had an airlock to do spacewalks. Not shown is the galley. Question about food. We ate very well. My favorite was rehydrated shrimp cocktail with horseradish sauce, which I ordered for every meal except breakfast. But we had dietitians that made sure that we had the right number of calories and the right balance. So I had my fish anyway, or my shellfish anyway. Altogether, it was also a very large cargo vehicle. The payload bay was about 2 school buses long, 60 feet, so every mission was different. We could carry up pieces of the International Space Station, or in this case was a laboratory that we conducted microgravity research in. My first crew trained 18 months together, 5 Americans, 2 German astronauts, Reinhard Führer, Ernst Messerschmitt, and Bubel Ockels from Holland. We had this lab in the payload bay, as I note there, 7-day mission. My second mission, I had the opportunity to operate the robotic arm, and we brought back a research satellite that had been in Earth orbit for 5 years, collecting data on space, ultraviolet, how do materials respond to ultraviolet light, micrometeoroids, orbital debris. If we want to improve the design of satellites we send up, or space stations, we need to bring data back. And that's what this did, called Long Duration Exposure Facility. We actually had a principal investigator from Texas A&M on that mission. My third mission was 13 days, and it was a space lab that also had microgravity research in it, material science, fluid physics, biotechnology, protein crystal growth, combustion, and a large number of medical experiments as well. And then I got a call in late 1993. I was actually at NASA headquarters working there. Said, we're going to partner with the Russians, where we're going to dock a space shuttle to the Russian space station Mir, and we're going to fly Americans up to Mir, and they're going to fly Russian cosmonauts on the shuttle. We'll do this for 9 missions, and if it all works from many perspectives, such as language, measurements, systems of measurements, politically, and so forth, we're calling it phase 1, we'll build a space station together. So I was one of the first 2 astronauts sent to Russia to train. I was a backup to Norm Sagard, but I trained with my own cosmonaut crew here, Anatoly Solovyev and Nikolai Budarin, and then became qualified in the Soyuz and the Mir space station. That was about a 19-month training flow. And then we docked. I came back, and Norm launched to the Mir. 3 months later, I launched on the shuttle. We docked. And this was the picture of first time we had 10 people together in orbit. This is how you do a group photo in 0G. So, and it was we had a great set of crews. We worked together. You can't tell who's Russian here, who's American. When you're working together and you're responsible for each other and your safety, you become a team, you become a crew. And we set that stage for further flights. By the way, this is what the Mir looked like when we docked. Unfortunately, after a number of years, a couple decades, it was deorbited because it was deteriorating. And so now we fly together on the station. But you can see it was a series of modules. We actually attached a docking adapter up here so the shuttle could dock. And then this picture was taken by the Russians in their Soyuz, just as we're about ready to dock from the Mir space station. You can see about ready and undocked. And this picture was taken of the shuttle from Mir, and all crew members claim it because we all took this picture. It was a window right there with a great view on the world. We did a number of medical experiments together, still continuing with the medical research, but we also had leisure time, and one of the cosmonauts played the guitar, and we all attempted to sing. You can hear this in an IMAX film. I'm not sure if those are real voices because we didn't sound that good, but that's okay. And then my last mission was the 8th mission to dock to Mir, STS-89. We actually had another cosmonaut on board our crew, Salajan Sharipov, who had trained in Russia for 7 years but took his very first space flight with us. The success of this program, called Phase 1, led to the commitment to build the International Space Station. By the way, this is our group photo once again. This picture I'm showing, let's see, so this is re-entry now, taken from the crew point of view. You can see our displays in the shuttle cockpit, and if you want a real close look at this, we now have the simulator at Lone Star Flight Museum down in Ellington Field near NASA, and that's been restored, so you can actually see what it looked like. No pictures of the actual re-entry, but this is an updated artist concept now from the one I just showed you. And it's a glider. It performed very well. Our crew did a nice soft landing in January of 1989, and this is just a 2-minute clip of launch in what we call the first stage, in case you haven't seen it. Worked just like we animated it back in the 70s. All those Rockwell engineers were really, really smart. Okay, and we didn't have all the tools that we have now. Great landing, sunset in January of 1998. And now we have a space station that we've had up operating for over 20 years. We have students that don't know a time that we weren't in space, that we didn't have people in space. It's a brand new world. It's the science fiction I was reading about when I was a kid, or the movie 2001: A Space Odyssey that I saw in 1968 as a freshman and went back to see 3 or 4 times, sitting in the front row watching that shuttle dock to this rotating space station. And there it is. It's up there. And now it's a platform that'll be there till at least 2030, and we're preparing for the future. So, okay, so what do you do next? Check, build a spacecraft. Check, fly in space. And I thought, well, you know, my mother would say, well, when are you going to retire? And I thought, well, I've done almost everything I would want to do. I haven't been to all the countries I've flown over. But I think I want to do for the youth what my teachers did for me, which is talk about what futures can be, how they can be part of that. And it's an exciting time to be a part of the future of space exploration, whatever your discipline is. Because this, you know, Apollo took a nation, hundreds of thousands of people, not just engineers and scientists, but managers, those who actually could negotiate international relations is also part of it. Everyone can be a part of it. So we have this beautiful station up there. If you don't want to go to the app, Spot the Station, you can actually learn more about it from the website, spaceflight.nasa.gov. It's a football field wide. That's why you can see it. The solar rays are very reflective, as well as the radiators. And it's pretty amazing what you can see from the station. I'm just showing some lightning here. and some auroras, and just some of the crews, the international crews. If you look at the partnership on the International Space Station, we're talking about more than 22 nations with the European Space Agency as well. So we have NASA, European Space Agency, the Japanese Space Agency right here, the Russian Space Agency, and the Canadian Space Agency that are all part of that. And I'm proud to say the shuttle helped to make that happen after its 30 years, 135 flights. Now, I did take a departure to Seattle. I was actually running the Museum of Flight, and we started a number of space programs there, but I still go back to Scotland. A group of us in 1998 started the Scottish Space School. These are some Scottish aliens that I met along the way. And then also, when I was at NASA, we started some university programs with our zero-G airplane called Parabolic Flight, so that was a lot of fun. Museum of Flight was very rewarding, and we reached K through 12, and so now I'm reaching back up to the 12 and on, right? So this is my lab here at A&M, working on two-phase fluid physics for partial gravity environments, as well as spacesuits. But what's next? When I used to show these slides back in 2016, I'd say Moon and Mars, but we had no program to go there. In 2018, the President signed Space Directive 1, which sends us back to the Moon and on to Mars in this kind of journey. We need science, we need technology. We're going to explore the Moon. We have a station. We're going to put robotic landers, again on the Moon, but also on Mars. All of that technology. Time frame, we're supposed to be on the Moon by 2025. The crew there's going to be a crew that's just going to go around the Moon. They're going to be selected on Monday. There's a big event. There'll be 4 people selected for that mission. That'll be really exciting. When are we supposed to be on Mars? If everything goes well, 2039. Not that far away, especially for young people, and they want to think about that. What might a lunar base look like? Well, again, for those of you who saw 2001: A Space Odyssey, it gets pretty close. We're going to have habitats, we're going to have laboratories, and it's not just going to be NASA. We've got companies that are now planning to land on the Moon. SpaceX is building a rocket for us, but they're talking about other applications. You're going to see commercial companies trying to extract water from the South Pole so that we have water to drink and oxygen for fuel. So this is called Artemis, and that's what you want to follow. It's called Artemis because that was the sister to Apollo, and Apollo was our first mission. This decade, so many different varieties of landing spacecraft, but it's going to happen because the technology we developed during Apollo is laying the platform for us to go back and stay, to do research, to look back at the Earth, to study the Earth. A great platform to really look at the Earth holistically, from a weather point of view, from the oceans, atmosphere. We're also going to build a new space station around the Moon. It's called Gateway. And eventually, rather than a mission going directly to the surface of the Moon, the astronauts will stay on Gateway, and they'll have what, sort of like dune buggy sorties down to the Moon. And they'll actually have vehicles on the Moon, too, that they might live in for 30 days, rovers. Then on to Mars. Mars is a lot harder to get to. I mean, we've got rovers there. We know how to land on Mars, but it's still a long mission. It might be 6 months to 9 months to get there, stay anywhere from 30 days. That's one of the recent design missions, to a year, 6 months, 9 months to get back. So you're talking about a 3-year mission, not unlike 200 years ago when the great explorers explored around our planet by ship, right? But they didn't have email. They didn't have the kind of communications we have. Now we can have a somewhat interactive environment with the crews on Mars, except the delay in time is about 40 minutes. So this might be what it looks like. We might put the habitat down first. The launch windows are 2 years apart. That just has to do with orbital mechanics. So you might want to put your habitat down first. And maybe this is a very thin carbon dioxide atmosphere, but maybe it scrubs the oxygen out. So you fill up the habitat first and you make sure it's livable. Then you commit your crew to it. But we need smart robotics. This envisions a robot that's actually being commanded by the astronaut to kind of follow along like a dog. Has life support systems in it in case your spacesuit fails. You get into it, maybe take your suit off. Many different concepts that we're looking at. So I mentioned the new announcement. There's actually a class after this, but this was the 2017 class. And you can see what they look like. They can read about them. They grew up just like these young people did, you know. But they did have a science and math path. That's really important. We select 3 classifications of astronauts: engineers, scientists, and medical doctors. So if you're also interested in medicine, this is the pathway. And particularly in Mars, we envision having a medical officer on the flight at all times, because there's no evacuation to an emergency medical post. And we'll have smart computers on board to help us with medical diagnosis. Well, new sensors, that's another area we really want to focus on, is diagnostic wearable sensors that monitor your body the whole time. So I had an opportunity to be at the launch for this last mission to the moon. That was pretty exciting. That was an unmanned mission. This next one will be a manned mission. And it's going to happen. So if you take the long view, because one of the things I liked when I was reading off the bookmobile is I also loved history, the history of technology. How did we learn to do this? Where did geometry come from? Who used it? We don't have textbooks from 5,000 years ago, but how did they know, right? And so I believe that as we build from generation to generation on this knowledge, as faculty, that's what our job is, right? To pass this knowledge on. And not only that, to inspire our students to learn how to learn, to question, to go to the next step. It's not always in a textbook. They'll be the researchers. They'll be the discoverers. So this is my take on it all. A great nation's health and prosperity depends upon the technological innovation, solutions to the problems of supporting life, and inspiration of its youth. It will depend upon the production and development of its scientists, mathematicians, engineers, chemists, physicists, astronomers, but also philosophers, poets, artists. It all goes together. But if you don't have the foundation of the math and science, you can't pull together the reality. That's what we do in engineering. We try to create the future that never was. Robert Goddard was a name I mentioned because he was born the same year as my grandfather. And when he was in his 20s, he studied physics, and then he wanted to go to Mars too. In fact, when he was in high school, he was the high school valedictorian. And he talked about wanting to climb to the highest tree and understanding what it would take to go to Mars. And I really resonated with that. You know, same thing, look at the sky, wonder what it would take. So he became a physicist. He gave a speech in New York in the 1920s, an invited lecture. And the next day, the New York Times wrote this scathing article. And it said, everybody knows, even the simplest high school student knows, that liquid-fueled rockets will not work in the vacuum of space. And, but that didn't deter him. He took his research to New Mexico. He's now known as the father of modern rocketry in the United States. But he died before he could see his rocket used. It was his wife who made certain that his patents came to bear. But on the day that the Neil Armstrong and Buzz Aldrin and the crew launched to the moon, the New York Times published a public apology to Robert Goddard. And so what was his legacy? Well, the Goddard Space Flight Center in Greenbelt, Maryland, that builds all of our great observatories that we send out to the other planets. His technology, his calculations, his physics. And if you also wander around the center, you'll find one of his quotes from his high school valedictorian speech. He said, "Who is to say what is impossible? For the dreams of yesterday become the hopes of today and the realities of tomorrow." When I gave a speech at Goddard, maybe 40 years ago, they gave me a little plaque with that quote on it, and I keep it on my desk to remind me that even as you get older as a professor, never to say it's impossible, You might say you want to check the math, okay, but never discourage someone from thinking outside the sphere. Thank you very much. So I believe that we'll take questions, right? Yes.
With the advancements in spaceship construction, Relativity launched a 3D printed rocket suborbital 2 weeks ago. What do you see as the future of spacecraft construction?
Oh, spacecraft. The question was about the future of spacecraft construction and 3D printing, and the fact that's being incorporated into some spacecraft. Well, you know, 3D printing is a very broad field, and spacecraft still require precision and reliability. So when they first started 3D printing metals, and I'm familiar with some work that was done by the Aerospace Corporation, they still had to ensure that the metal had the integrity, the strength, and the anisotropic properties so that it wouldn't fail, right? So as the technology matures and we can still find ways to certify and validate that, there are advantages to 3D printing in terms of complex parts, for example, or multi-layer materials. So I think it's really just up to us to advance the technology. Yes?
So, like, when you first came back from space on the first mission, like, how did your body learn to, like, adjust, and how do you see that kind of helping astronauts adjust after their first mission in space back on Earth? How do you see that kind of thing?
Yeah, so the question is about adjusting after a space flight. So we could probably have a whole different, another hour lecture on the effects of microgravity, we call it, on human physiology. And it depends, the effects are whether you're on a short flight or you're on a long flight. So on a short flight, there's always some changes to your vestibular system, your balance system, because you have two sets of organs in your brain. You have your otoliths, which are kind of your vertical, and the semicircular canals, which is kind of rotational. And when you're up in orbit, we think that some disturbances there help. They may cause nausea the first couple days, then you recover. Some people don't feel well when they land, but you recover very quickly. One of the concerns we have right now, though, is if you're on the gateway station for a long period of time, let's say 30 days, and then you try to land in 16G on the moon, are you going to have some vestibular disturbances? Those are short term. Long term, I didn't talk about the Skylab space station that we had in Earth orbit in the 70s. That's where we first learned about loss of bone that mimics disuse osteoporosis. And every astronaut right now exercises about 2.5 hours every day. And we care about the diet because we exercise we're up for 18 hours. We're working against gravity all the time. And if you've got the right diet, you shouldn't be experiencing bone loss as long as you've got exercise, diet, and some of it's genetic. But we want to make sure that when astronauts arrive at Mars, that they're as healthy as when they left. And then when they get down into 3/8 gravity of Mars, because the moon's 1/6 and Mars is 3/8, that load itself won't cause fractures. So there's short-term effects and there's long-term effects, but there's cardiovascular effects because your heart's not working as hard. There's immune effects that we're still trying to understand. So there's about 6 different systems that are affected. Yes?
It's a two-part question. So whenever you had your first launch, when you went up into space, how was your reaction when you first started, like, floating?
What was my reaction when I floated? I really felt at home. You know, I watched a lot of movies too, but you have to be careful when you first encounter this microgravity environment because you are just floating in air by not moving your head too fast when you first get there because you don't want to, what we call, provoke your vestibular system. But if you move, your body is very resilient. If you move slowly, you get accommodated to it. I acclimated pretty rapidly. And I was okay on all my 5 flights. But you cannot predict it. We call it space adaptation syndrome if you don't feel well the first 48 hours. But you can be the most experienced fighter pilot out there, perform acrobatics every day, and get to orbit and not feel well. So we don't know how to predict it yet. We medicate it, and we ensure that the first 2 days we are pacing ourselves, so we're not moving too rapidly. And we also train with a backup. I might be launching a satellite like on the shuttle, but I'd also have another crew member who could do my job as well. So I didn't feel well, then I had a backup to do that.
If you could go back to space again, would you?
The question is, if I could go back to space, would I? Absolutely. So, I keep thinking about John Glenn. And, I think about, they want to look at gender differences, right? So maybe it's 77. So, yes, if they asked me, yes.
What medical monitoring devices are you planning to build into spacesuits?
Medical monitoring for spacesuits, that's a really good question. They'd like to build in, we used to have ECGs all the time, so that's not new. But one of the discussions I just had this week with some folks at JSC, we have a liquid cooling and ventilation garment. If we could put instrumentation into that, because that's next to the skin, localized thermal monitoring and also localized thermal control. Because right now your temperature control is one valve. And so you might be hot on the top and cold on the bottom, but it's not going to adjust to a local environment. So you'd want to get as much as you could with wearable technology, right? Oxygen, PPO2 on oxygen, blood pressure if you could, all of those things, especially for these long EVAs on the surface of the moon and Mars. You want to work with me on that? Okay, you give me a call. Yes.
Okay, so you mentioned the astronaut class. So if you're chosen as part of an astronaut class, how long does that class last? Is it a year? Is it 3 years? I mean, in the rotation of being picked?
Yeah, it's a good question. How long does it take to fly once you're part of a class? It really depends on the tempo of the vehicle that's flying. I was very lucky that, I was selected the year before the first shuttle flight. And then although the first couple of years it was 2 flights a year, they have a minimum year training as a class. And that means we're in the classroom too. I'm learning astronomy. All the astronauts have a leveling set of courses they take. So astronomy, and the fighter pilots learn material science because we do that research on orbit. And then it depends on the tempo again. So I had my first flight in '85. That was 5 years. But then it went, then we had the Challenger accident. But then I flew 90, 92, 95, and then 98. And that was a pretty fast tempo after I flew. The first flight just depends what vehicle's available. There's no set time frame.
So everybody that's picked for the class is eventually going to fly?
Yeah, that's a good question. Is everybody that's picked going to fly? NASA puts a lot of effort into selecting in rather than waiting till you fail out. So they want to make sure that that the investment in training is going to result in success. So it's medical, it's psychological. A lot of, the average age when I was selected was 35. Okay, so they have some record of your performance as team members. They look for people that have been parts of teams, especially sports teams. It doesn't have to be engineering teams. They want to know how you've historically responded to stress, those types of things. So they'll look at that whole record as they invest in you, because it's, as you might imagine, you're investing millions of dollars in simulators and all this other time. Yes?
In a lot of those pictures, it looked like there was a lot of men. What was it like being a woman?
That's an interesting question. So what was it like being, I was on 2 crews with 2 women, a lot of men. Like I like to say, I had a father and 2 brothers, and I thought they were pretty regular people. And so I've worked with men all my life. And I didn't look at it that way. And I was never treated differently as long as I did my job. And I think it's really important for young women to understand that you're not walking in with a penalty. There's a lot of people there trying to help you succeed, but you have to do your part. You have to be part of the team. You have to be skilled at what you're doing. And if you're part of the team and you're skilled, then they look at you that way too. So,
one of the things that I'm most likely to hear for you was when you were in the range back when you were a kid and look into the Milky Way and think outside the box. So growing up, what kept you going forward? Was that feeling when you were a kid?
Oh, what kept me going? I think dreams keep us going. I've talked to a lot of students, and those that can get through the rough parts, because life is going to have some rough parts, right? is if you have that dream and aspiration and you're doing it because you want to do it, it's that inner drive, not because someone else thought that was the thing you ought to do. That's what kept me going, was that potential. And now I recognize that when I had this dream out there, you know, we weren't flying in space. You know, they weren't selecting astronauts. I wrote my first letter to NASA when I was in high school, and they said, well, we recommend you get a college education first. But they answered the letter, right? That keeps you going. But I had off-ramps. I said, okay, if I can't be an astronaut, what could I be? Well, it was, you know, being an engineer, working on spacecraft, and then when I went to NASA, if I wasn't selected in 1980, it was, oh, I'm going to be a flight controller. I'm going to be a Gene Kranz, that type of thing. You want to have off-ramps in your life so you're not totally, you know, destroyed by your first disappointment. Yeah. There's one back there with. I can't quite hear that. Something interesting?
What was the strangest thing you did in space? The most interesting thing you did.
Oh gosh, how do you do that? I had the opportunity to train with.
What was your question?
What was the most interesting thing I did in space, right? That's a hard question to answer. I trained with researchers who had their experiments on the shuttle from all over the world. So I got to go into some incredible laboratories. I mean, you know, Scripps Institute, MIT, we had Texas A&M, just, you know, great places to learn all this knowledge, the classes you couldn't take in college. And all those were interesting. But I will tell you, my first flight, perhaps the one image that sort of sticks with me, because you never know if you're going to have a second flight, right? You say, I'm going to take advantage of this first flight. And we had a unique attitude of the shuttle such that the tail was pointing towards the Earth and the nose was up. And we have these big overhead windows, and they were facing in the direction that you're going, so you couldn't see the rest of the shuttle. It was just like you were at a picture window and you're in space. And we had a very high inclination, that's with respect to the equator, so 57 degrees north and 57 degrees south, which means we could sort of look down on the north and south poles. And on that particular mission, which was October of 1985, the southern lights were really, really active, Aurora Australis. And when you look down on it, it was like the South Pole was on fire. It was like, and because we were kind of at what we called the terminator between dark and light. I felt like I was watching a movie. And I thought, well, I'll just remember this. You know, I'll get about a minute or two at the window. If I never get to fly again, I could say I could snapshot that. So maybe not interesting, but you want to keep that in your memory. You'd like other people to see the Earth that way. It was really interesting. Yes?
What is the physical training like to get ready?
What's the physical training like to get ready? Well, we have an astronaut gym. First of all, to be selected, you go through a suite of tests, and you don't have to bench press 600 pounds. You need to be cardiovascularly fit. You need to have a minimum strength capability to operate in the suits, which were at pressure. And we have a gym to stay fit. We're expected to stay fit. And then before flight, if we're selected for a flight, we go through another physical assessment. Now, if you are assigned to a space walk in these pressurized suits, we also have a training regimen for that, and that's pre-flight, because it takes a lot of torque and force to bend the arms on these inflated suits. Now, when you're on orbit, and I was just at the NASA JSC facility that designs the exercise equipment for the crew on board, they do both cardiovascular as well as isometric exercises to maintain muscle strength as well as bone integrity. And that's very rigorous. They didn't tell us when to go to the gym before flight. We're expected to maintain our health. But when you're on orbit, you are timelined every day to be in that physical regimen for 2.5 hours, and they monitor that. But then they also look at everything else, your blood pressure, blood samples, trying to keep you healthy. Yes?
So when you're like on the space station or in orbit doing experiments, do you sort of become pretty like broad doing all types of experiments, or do you stay pretty specialized?
We have to be broad. Let's say that on my first flight, which was sponsored by West Germany, we did most of our training there. We had almost 100 experiments that 5 of us trained on. And we trained on in the universities or in the government labs, but not all of them required us to interpret results. But we had to understand what the objective was. Okay, so it might have been in fluid physics, for example. In some cases, you're expected to observe the phenomena, you know, what looks unusual because the PI is not there right there. But that's what made it interesting and fun. It extended the training time, but you know, you were part of the team. Now, in terms of the medical experiments, you are an operator. You know, I took blood on, you know, I have my phlebotomy certificate, so I take blood. Don't try me now, but, you know. And I did echocardiographs. We trained to be able to use an echo to look at your heart and capture those videos. You get much deeper training when it comes to the biomedical side of it. Just depends, yeah.
What was a major psychological barrier you overcame when going to space?
What was the major psychological barrier going into space? Not going into space, but it had to do with training. And it actually goes back, I worked for Boeing for a period of time very early in my career. I was doing some graduate work at the University of Illinois, and a bunch of the graduate students all decided to go to Lake Michigan for the weekend. And I knew nothing. I grew up in an area where we swam, but not a lot. And we went out to, 5 of us went out to what was supposed to be a sandbar, and it wasn't there. This happens in Lake Michigan, and it was a long swim back. And I'm really glad one of the other guys was a lifeguard because we were all pretty spent. And then I got this kind of phobia about water. And so you talk about what drives you forward. So I was working for Boeing. I realized I had to get over that. I had to be able to get my face back down in the water. So I joined the Boeing Seahorses Scuba Club to kind of force myself to do it. And that was hard because I knew I had to kind of get over that. If I wanted to be an astronaut, I was going to be spending time in the water tank, right? And I'm glad I did that because the first year as my astronaut class, part of what we did was not only get certified in scuba diving, but we had to go out on one of these ventures off the coast of Florida type of thing. And but still, you know, that first dive, you know, I'm sitting there mentally going, okay, it's going to be okay, it's going to be okay, and then get used to it. But that's part of the training regimen, you know, even though we're not in water in space. So, yeah, sometimes you just have to tackle your demons, right? Go do that. Yeah.
If you could go to any planet, which one would it be?
Which planet? Well, Mars. You know, we're lucky. We're the 3rd planet from the sun. It's the 4th planet. It's the only one really that we could survive on. It's not a big gas planet. And we've got a place we can practice on called the moon. You know, it's at vacuum. It's got some of the extreme environments. And so we can, and it's only 3.5 days away. So we can figure out how to do things in that 1/6 gravity and the harsh environment. It'll help, we call burn down risk, reduce risk to go to Mars. I will tell you a short story. When I was reading books, I read this science fiction, well, it wasn't science fiction, it was about a kid who was very, very bright, and he told all his neighbors that he lived on the 3rd planet from the sun, and they thought he was an alien. So I tried that on my school bus once, and they were right. Most people didn't know you were on the 3rd planet from the sun, but anyway, yeah.
What do you think about commercial space flight and its potential compared to government-sponsored space flight?
The question is commercial versus government, and actually it's a false comparison, and I'll tell you why. If you look at the history of aviation, so the Wright brothers tried to sell their airplane, and nobody would buy it, but the government signed a real small contract, so we'll figure out something to do with this airplane. And the airplane grew as both government and commercial, and so we have both now. And one of the mandates of NASA is to enable the commercial environment. So we started communication satellites, that's now commercial, right? So we want to buy services from the commercial sector. We're going to buy transportation to the station and buy rockets. But our mission is to get to the moon and develop the moon and then onto Mars. And hopefully in 100 years, there'll be other space stations, you know, out maybe towards Mars. So Are we okay on time, or we need to wrap up?
Yeah, I mean, we're okay.
Okay, we'll take one more here.
Do you believe like extraterrestrial life exists like outside or like out like somewhere in space?
So the question is about extraterrestrial life. And so let's define life. You know, life can be microbial, called extremophiles. We have those on Earth. Or someone like us walking around, okay? Well, I think the community says it would be, statistically thinking, there's probably some sort of extremophiles out there because we start finding complex, I think, amino acids on comets and so forth. So why would we think this was the only planet where something started to evolve? If there's something more complex, I can't say no. You know, I don't know. You know, there's long distances out there. They're getting longer, right? Our universe is expanding. So maybe it's getting harder, but who knows? And that's why it's so important for us to continue to explore and understand maybe it's a different form, that type of thing. Does that help you? Doesn't give you a definitive answer. No, I haven't seen any alien life in orbit. I'll answer that one now. Yeah. Okay, thank you very much.
We're over here with the barrels where I heard the big boom. So let's go ahead and ask and see what all that was about.
Hi, yes, so the barrels, the way it works is that we have a bottle, a 2-liter bottle of Coke or something like that, and then we put liquid nitrogen inside. Liquid nitrogen, and right now when we pour it in, it's in liquid, as you can tell from the name, liquid nitrogen, but whenever it starts expanding, it becomes a gas, and then it creates pressure inside the bottle, which then causes it to explode. Once it explodes and we put it inside, it causes the water to also explode.
Oh, wow. Okay, that sounds like a bigger version of that. So what makes the liquid nitrogen expand?
So it makes it expand because it becomes a gas. So gas is, it has a greater volume than the liquid. So it causes it to expand. The heat causes it to become gas,
okay,
which then creates the pressure and causes it to explode.
Oh, I see. So it's like if you heat up ice, it'll become water and then steam, and then boom.
Yes.
Oh, I see.
Not as fast as liquid nitrogen.
Sure, yeah. All right. So what he just explained right now is after they drop in the liquid nitrogen filled bottle, that explosion is going to reach all the way up there to almost, if you can see that guy on the garden. That container right there, the shiny silver one, has the liquid nitrogen in it. You can see some of it evaporating off as a gas, and they're pouring it in these styrofoam cups. Styrofoam because it has good insulation. This is a reason why you would keep your cold drinks or hot drinks in them whenever you go get food out to go or whatever. So there's some liquid nitrogen there, and they're going to put it in a bottle. You'll notice everybody is wearing gloves and safety goggles. All of that is very important. Safety is a priority. Now that all the liquid nitrogen is in there, they're having to screw on the cap very quickly and tightly. Here it comes. You can hear it crackling. And that's a depth charge. Do that every hour. All right, moving on, let's see if we can find Dr. Ed Fry. He'll tell us more about the festival. Dr. Fry, it's good to see you again.
Yes.
So, could you tell us about the festival, like how long it's been going on, what all it has to offer, how many people show up every year?
Yeah, well, I became department head in 2002, and it was, I forget now whether it was 2002 or 2003, but anyway, we had Stephen Hawking coming for a visit.
Really?
Yes. And I thought, since he's going to give a talk, we should maybe do something to get people interested. And so I sent a message out to all our faculty to get together with their students and put together a demos that students, visitors could come and see the demos and so forth, and then go to Hawking's talk, and then go to it afterwards too. And a bunch of the faculty actually did that. They got their students to do things, and it worked so well that the next year I decided we'll do it anyways, even though Hawking's not going to be here. And once again, it went over really well, and we've done it ever since. And it's been incredibly successful. And one of the reasons why it's so successful, I think, is our students do it. The students come up with ideas for demos, and then they run them on. You can see all the demos on around here. A lot of those are student ideas that they've come up with.
Yeah.
And so it's really fantastic, and the students enjoy it. And not only is it good for the visitors to learn about science, but in hindsight, it's now been clear that it's a tremendous benefit to our students.
Yeah.
Because the best way to learn something is to explain it to somebody else.
Yeah, that's true. That's true.
And so our students are getting a lot of benefit out of explaining all this stuff to visiting kids.
Yeah, yeah.
And so it's a fantastic thing.
Yeah. One of the go ahead. Sorry.
Well, okay. By 2006, it had grown so much. I was department head. I couldn't handle it all, and I asked the dean if I could hire somebody, and he said sure. And I hired Tatiana Rukamova, and she took over, and she has done incredible things with it. And she formed the DEEP program, Discover, Enjoy, and Explore Physics. That's what DEEP stands for. I don't know whether you've seen that on shirts. It says DEEP on some of the shirts.
Yeah, some of the shirts have DEEP across them. It's the group that more or less puts together all the demos and coordinates everything.
Yeah. And DEEP stands for Discover, Enjoy, and Explore Physics.
Yeah.
Or maybe it's Discover, Explore, and Enjoy, or Explore, Enjoy, and Explore. I'm not sure which way it is.
Tomato, tomato.
Yeah, right. But so it's done extremely well, and I think a lot of people benefit from it. And we've been shut down because of COVID for 2 years, and so this is the first time again. The last time we had it, we had a little over 7,000 people here. I think we're doing pretty good again this time. There's a lot of people here. And they don't just come from Texas, they come from everywhere.
Yeah, I've heard they come from states abroad.
Yeah, right. And in fact, actually, one of the stories I like to tell is, maybe it was 10 years ago, I got a call from a guy from Baltimore, Maryland, and he said his wife had been in College Station the previous year, and we had this thing called Physics Festival, and she told him about it, and his son wanted to go to it, and so he wanted to check on when the date was and everything, and so I told him, and he said he was going to bring his son and his son's best friend from Baltimore.
Wow.
For the Physics Festival. And actually, a couple days before it, I got another call from him, and he said, "I just heard there's going to be a talk for Physics Festival on Friday evening. Is that right?" And I said, "Yes." He said, "Oh, we got tickets for early Saturday morning. I'm going to have to change him." He changed his tickets to Friday so he could come to the Friday talk.
That's awesome. Yeah, one of the things I personally really appreciate about the festival is not just seeing the passion that all the students have in putting together their demos and explaining it and whatnot, but I think this really if there wasn't already good curiosity in science and learning new things, that this sets a spark in a lot of people seeing
think it
things.
does too, yes. I've actually seen students that after physics festival, they'll make comments, you know, I think maybe I'm going to become a physicist. Because they enjoy it so much.
Yeah, it's a lot of fun.
Yeah. And the thing is, we focus on kids. And our students do the demos.
Yeah.
We do have faculty helping out and so forth, but and so it's, and Tatiana took over in 2006, and she has just been incredible. She's the one who actually started DEEP.
Yeah.
And called it DEEP. Yeah. I'm so pleased with it all because it's just amazing how it's grown, and and I think it does a lot of good.
Yeah, I do too. I think it's really important for everybody to, you know, at least have an understanding and appreciation of science, because I mean, it's what's given pretty much everything we use on a daily basis.
Oh, yeah, right.
So,
and it's amazing how many people there are around here, isn't it?
I know, it's crazy.
Inside the buildings too.
It's packed shoulder to shoulder in there.
Yeah.
And we'll see that at some point shortly.
Yeah.
All right, well, thank you so much.
Okay.
Have a good one. All right, so we'll continue the rest of our filming by going around and showing off some more cool demos.
Thank you.
All right, let's see here. We'll start with some of the angular momentum demos over here. Angular momentum, in a nutshell, is a tendency for something that is spinning to want to continue spinning. So let's check out some of these things and learn some more. All right, so over here we have, looks like people spinning on stools, and they've got little hand weights. Let's ask what this is about.
Hi there.
Hey, how's it going?
It's going pretty good.
Awesome, awesome.
Yes, sir.
Not burning up too much out here?
No, I mean, it's nice weather outside, so it's pretty chill. Yeah.
It is,
yeah.
it is, and being in the shade helps.
Yeah, Tommy, that is very correct. That's very correct. Yes, sir.
So, I noticed people were spinning around here.
Yes, sir.
What's going on with that? What's the science behind it?
So the concept behind this is angular momentum, right? So as you're spinning, we impart a momentum on you, right? And as you impart a momentum on you, that momentum is conserved. And so then as you bring your arms in and arms out, there's an equation called, it's actually right there. I don't know if you can see it. It's L is equal to I omega.
a little faster.
And what happens is that the I corresponds to your radial distance from your axis of rotation. So as you decrease that radial axis, you spin faster because that momentum is always conserved. So whenever you conserve that momentum, if you decrease your radius or your radius, you increase your angular momentum in order to keep that, you increase your angular velocity to keep that momentum conserved. Oh, you can go ahead and pick that one right there.
All right.
I will give you the larger weights right here.
All right.
How you're gonna?
Why don't you take the mic for a second?
Sure, I guess. Here you are. All right, so I want you to hold out your arms like this. I'm going to give you a little spin, all right? Now, as I spin you, I want you to bring your arms closer together. All right. And you'll notice that you spin a lot faster, right?
Yeah.
Now I want you to bring your arms out. And there you go. And you spin a lot slower, right? Your radius has increased, and therefore your angular velocity decreases in order to keep your momentum conserved. As you bring your arms down, or as you bring your arms closer, your radius decreases, so your angular momentum increases to keep that momentum conserved.
This is harder than it looks.
Yeah, sorry. There you go, sir. You feeling dizzy?
A little bit.
There you are.
Thank you so much.
Yes, sir. I hope you enjoy the festival.
Thanks, you too. All right, so I'm a little dizzy, but we'll try and hobble on over here to another angular momentum demo. Hi, how's it going?
Well, thank you.
So we noticed this suitcase wasn't really like that when they were holding it.
Right.
Would you be able to tell us why that is?
Well, yeah. First of all, so try picking it up.
verify that it's a normal suitcase. Nothing.
Feels like a normal suitcase?
Straight line, come back, turn around. Another day, another dollar, right?
Yep.
Now let's set it down.
All right.
Try again.
Try again?
Try again, see what happens.
Okay, it's upright. Whoa, whoa. Oh, wow.
What is going on there?
I have no idea.
It's the same briefcase that you were holding a minute ago.
It's alive.
But it's alive, right? It's fighting you. When you try to turn it one way, it wants to go back the other way, right? So, I have a massive flywheel that we spun up, right?
Okay.
And once it's spinning, it has a property known as angular momentum. And that's a conserved quantity. So if you try to change the position of the briefcase, then it's going to impart a force on your hand.
Oh, I see. So this thing's spinning, say when I picked it up right, the wheel was like so.
Right.
And every time I tried to turn,
you were changing the plane.
I was trying to make it do that, but it didn't want to do that.
Correct.
Ah, that's really neat.
Yeah.
And what about this?
So this is a related concept also having to do with angular momentum. So if you want to go sit in the stool for a minute.
Okay. I'd already sat in the stool.
Well, you're going to sit again and do something different. So.
Oh, okay.
Have a seat.
All right. Excuse me.
You're going to need 2 hands for this, though.
I will. Okay. Would you like the mic, or do you need 2 hands?
That's fine. So I'm giving you a bicycle wheel. You're sitting on the stool. You're going to turn your hands 90 degrees one way, the other. Right? Turn it the other way. Nothing happens, right?
Right.
So now I'm going to spin the wheel and give it back to you. Right? When I give it back to you, just make sure it doesn't touch your arms.
Sure.
Unless you want a nasty scar.
Gotcha.
Which we will not be liable for. Hands out. And now turn the wheel. And if you want to stop turning, you'll just bring it back to the original position, right?
Nobody's funding.
And if you want to go the other way, you turn it the other way. So again, that's conservation of angular momentum. The wheel has some angular momentum with a preferred vector, right? The preferred direction. And then when you turn it, you and the lazy Susan go the other way so that the sum of the angular momentum remains the same.
Very.
All right. Thank you.
Thanks. That's really neat. I wonder if you could use something like that to turn a spaceship or something.
This is called a Heron's fountain. So basically what happens is I'm gonna pour water into the top. It's gonna drain down into this bucket, and when it drains, it pushes on the air. The air has nowhere to go but through this tube. Now when the air gets pushed through this tube, it pushes on the water because the water has nowhere else to go but into this tube, causing it to shoot out the top.
It just keeps going?
And it keeps going until the water levels reach almost equilibrium. So this one gets really high, this one gets really low. And a cool thing about it is the higher you lift up your top bottle, the faster it'll go. And if you lower it, the slower it'll go, and it'll stop because their water levels will become similar.
Oh, I see.
Yep.
So could this sort of thing be used to generate electricity?
I think potentially if you do some sort of work with water, but
it's not like it could keep going, right?
no, you have to keep restarting it.
Ah.
Yeah.
Those don't exist as far as I know.
So here we go. It should, yep, pushes on the water, and it just will keep going until the water levels change.
Oh, wow.
And this is more for just design purposes,
Sure,
make it
yeah.
fun and colorful.
Yeah, the idea is so that water comes down here, and because this is filling up, air wants to come out, pushing on this one, and that makes the water rise through this guy and onto the little pinwheel. Ah, very neat. Well, thank you.
You're welcome, thank you.
What's up? How's it going?
Hey, good. How about you?
Pretty good, yeah.
So, why are we sticking potatoes in straws?
So what's happening?
The other way.
Yeah, the other way around. It's a long day. So basically, let me grab a straw. we've got a bunch of straws. Oh, that one's broken. Okay, well, gosh, it's crazy over here. So basically normal straws are pretty flimsy, right?
Yeah.
And so we try to stab and it's not gonna go in.
Okay.
But if we put our thumb over the hole and we go, all this air is getting trapped inside. And so what's happening is it's building up pressure and it's reinforcing the walls of the straw. And so it's making it super duper strong and so we can stab right in.
Wow.
So what we're teaching is that the way air pressure can reinforce a tube of some sort of material. So yeah, physics.
Okay. So when you try and put the straw in without putting your thumb over it, it'll just bend. The air
Right,
gets out of the way.
yeah, because it has no support.
Okay.
Yeah.
But when you're covering it, the air doesn't have anywhere to go once it touches the potato.
Yeah.
And so it just goes right in.
Exactly.
Wow.
Yeah.
So, do you guys cook the potatoes after?
You know, I've got no idea. We're gonna recycle the straws though, save the turtles.
Oh, okay. That's
yeah.
All right. Well, thank you so much for your time. Likewise. All righty. Now, I remember seeing over here earlier, some people are crushing cans with fire and water. That sounds like fun. The potato and straw one, I don't know if you can do that one at home or not. You'll have to ask your parents if you're younger. Might be fine. Wow. Howdy.
Oh, hello. Sorry.
So what is this plate, cup, tube, ball construction?
All right, so what we do is that we have a plate with a cup, a paper towel or a toilet paper roll, and a tennis ball on top, and then you're gonna give the plate a nice whack with your hands. Well, and then the ball falls straight into the cup. So moment of inertia is the main concept here. So basically, the ball is at rest here. We push the plate out horizontally, and the ball has no choice but to move straight down due to gravity. It's always going to move straight down due to the moment of inertia. Yeah.
I kind of want to try it.
Yeah, definitely. Yeah, there you go. First try.
Awesome. Thank you. What is this? Hey, what is this?
So basically, right, we have here an experiment, and so I guess I have a question for you guys. So let's say that we were to spin this, and I guess they're about to. Do you see the ball going inwards?
Yes.
Most people would think that the ball is going to go outwards because, you know, you're driving a car really quickly, you take a sharp turn, you get hit to the side, right?
Sure, like you have a ball on a string, you twirl it around,
the
it goes
centripetal
outside.
force. But what is actually being pushed outwards is not the ball, but rather the water. And so the water is like kind of putting a force on the ball called buoyancy, which is like when you float. And that buoyancy force is pushing the ball back inwards.
I see. Okay, so it's kind of like both want to go outwards, but because the water's heavier, it goes on the outside.
Exactly.
Ball floats to the other.
Yeah, floats, exactly.
Ah, okay. That's really cool.
Yeah, thank you.
Could this work with like gases instead of liquids as well?
Yeah, so I don't know if you've ever like driven a car and you have a balloon and you accelerate. A lot of people think that like, oh, you're driving so the balloon's gonna go back, right? But the balloon actually goes forward because like the density of the air and the weight, and it pushes the balloon forward instead of backwards.
Oh, that makes sense.
Yeah.
Okay, so this is something you could see if you've got a balloon in the
Yeah, anyone can do it. Just don't speed. Or,
yeah. All right. Well, you can see science everywhere. Thank you.
Thank you.
So I see something dangerous here. There's a blowtorch or something, and a can, and a fish tank. Did you crush that can?
No.
No?
The air inside was heated.
Oh, you can see it. This is very small, but this is...
The air inside was heated. We submerged it in this colder water, and the air temperature inside rapidly decreased, and so did the air pressure, which creates a vacuum inside the can. And since our surrounding air pressure is much greater than what's inside the can, the air wants to get inside the can, but it can't since we sealed it from the bottom. So it crushes the can immediately as soon as the temperature inside cools.
Oh, okay. So you put some water in there, you heat it up to make steam, and now it's warm and atmospheric, but as soon as you put it in the water, it cools down and shrinks.
Yeah.
Okay.
It contracts as the pressure inside decreases.
Oh, cool. Could we see it again?
Sure. Yeah.
From this, you get some sense.
Alright, so we just heat it up for about 15 seconds.
So they're heating the can now with the water inside, and you can see a little bit of steam coming out the front. Would you look at that? Do you have a name for this demo?
It's just a crushed can experiment.
Crushed can experiment.
Using atmospheric pressure.
All right. So why do we have these scales here?
So what these are is they're scales showing what the same weights will weigh on different planets. So the way things work, the way gravity works is that every single planet will have a different surface gravity. So the same weight will effectively weigh different things on different planets.
Okay. So could you show us an example of this then?
So this scale shows how much the Earth, something will weigh on the surface of the Earth. So if we put a 30-pound weight on this scale, it's about as expected. It goes to 30 pounds. Now, the moon is about, it has a surface gravity 6 times less than that of the Earth. So obviously we would expect something on the surface of the moon to weigh less, right?
Right.
So, and it would actually weigh 6 times less. So if we put something on the moon, it's 30 divided by 6, which is about 5 pounds.
About 5.
Yeah. So now if we move even smaller, we get to Halley's Comet, which is, comets are just pieces of rock flying through space. If you put something on, and Halley's Comet is about 3.5 miles long, so it's about the size of College Station. It's not really all that big. So its surface gravity is actually quite low. It is 100 times smaller than that of the moon. So if we put something on Halley's Comet, it only weighs 0.05 pounds, which is 500th of a pound. So it's tiny. You could probably lift a car on Halley's Comet if you wanted to, since it just really wouldn't weigh all that much. And then on Jupiter, Jupiter is the biggest planet in our solar system. And Jupiter, it is 10 times bigger than the Earth in size, but Jupiter is made mainly of gas. So its surface gravity isn't like 10 times bigger either. It's actually only just 2.5 times bigger. So if we put this 30-pound weight on Jupiter, we get something about 60 pounds, which checks out. So yeah, what this also means is if I drop this weight on Jupiter as compared to Earth, this weight would fall 2 times faster on Jupiter than it does on the Earth.
Faster, and these would be slower.
These would be much, much slower.
Okay. Yeah, that makes sense. You know, you see videos of astronauts on the moon, and they kind of float. Yeah. So does that mean that there's a difference between weight and mass?
There is a big difference. So weight is different relative to wherever you're standing on, relative to whatever gravitational field you're closest to. Your mass is always going to be the same. So this will always be 30 pounds in mass. What we measure it on different planets will just change.
Ah, I see. Okay, very cool. What about the, oh, that says Earth. That's an Earth one already.
Yeah.
Okay.
That one's broken, so
Gotcha. Well, thank you.
Thank you so much.
Have a good day.
You too.
Yeah, I totally. All right.
Wait,
there.
Where?
Right on your right. Yeah, that open spot. All right, we all got one? All right, we all good? Yeah. Good? Howdy! Oh, come on, you can do better than that! Howdy! There we go! Are you all ready for the grand finale? Let's go! Ready. Bucket 1! Bucket 2! Funnel! Cut! Fire in the hole! Come on and get a ball, everybody!
All right, good afternoon, everyone, and I hope you've all had a fantastic day today here at the Physics Festival. Thank you for joining us for this final lecture. As Nick mentioned, I'm Emily Levesque. I'm the author of the book, The Last Stargazers, and I am a professional astronomer. So if you've been watching the trivia roll by, sort of as you came into the room and sat down, you maybe noticed that it's been asking some kind of unconventional questions about astronomy and about how we study the universe. Over the next hour, you're going to be seeing answers to each of those trivia questions and the stories behind them. If you read about today's event in the program and the description of this lecture, you know that I've promised you these stories of just like wild Indiana Jones-like behind-the-scenes adventures of what life is like when you study space for your job. So I thought I should start this lecture with the most heart-pounding thing that's ever happened to me at my job, and it was a question that I got asked. You can imagine the big questions that we get asked in astronomy. They're scientific, but they're also almost existential. They're really big, deep questions. We're trying to answer things like, who are we as a planet? Or where did we come from? And are we alone? But the most unnerving thing I think I've ever been asked in my job is, have you tried turning it off and on again? So this does not sound deep or terrifying. This sounds like every annoying phone call you've ever had with your internet provider. But this question was terrifying because of where I was when I was asked it. I was sitting here at the Subaru telescope atop Mauna Kea Observatory in Hawaii. This is one of the biggest telescopes in the world. It has a mirror that is more than 27 feet from end to end. So just to give you from scale, here's me, and here is me standing underneath a 27-foot mirror, just so you have a sense of how big this telescope was. So I was working at this observatory, getting some data on galaxies billions of light years away for my PhD thesis. The night had been going great, the telescope was running and doing its job, and then in the middle of the observing, one of the computers in the room made this terrible kind of blunk sound. And I looked over at it, and then I looked over at the only other person on the mountain with me, who was the person in charge of operating this behemoth building-sized telescope. She looked at me and didn't look too reassured. And I asked her, what was that noise? And she said, it's okay, I think it's fine. I think the mirror is still on the telescope. And this was not as reassuring as I think she hoped, because I didn't know the mirrors could come off. So I asked her to explain. In this picture of Subaru, you can see sort of a big flat blue area near the bottom. That's where that big 27-foot mirror is sitting. High above it, you can also see a ring with, if you look very closely, a smaller black thing inside. Now that small thing is the secondary mirror of the telescope. When the telescope is working well, light comes pouring into it from above, it bounces off the primary, then bounces off that secondary mirror, and is directed into a camera or scientific instrument. The blunk sound we had heard was telling us that the mechanical supports holding up that secondary mirror had failed. And it meant that if we tipped the telescope a little far to one side or the other, we were at risk of that secondary sliding off the telescope and plummeting dozens of feet to the floor. And that's if we were lucky. If we were unlucky, it would hit that 27-foot primary mirror on the way down. So I had no idea that this was even a problem telescopes could have, but I was suddenly in charge of deciding what to do. We called the engineers who were in charge of running the telescope, and they immediately said, "Oh, you're probably fine. It's probably a false alarm. It's probably just an issue that we've run into during the day." They kept saying probably. "You can probably fix this by turning the telescope off and back on again." And it seemed really impolite to say, you know, I fixed my home internet this way. I'm not sure I want to fix one of the biggest pieces of glass in the world this way. But this was my problem. I was now in charge of deciding what to do. And all I could think of was I was running through stories in my head of the things that had gone terribly wrong at telescopes. The one that I was most remembering was this telescope. This is the Green Bank Radio Telescope in West Virginia. It's a radio telescope rather than observing the light we see with our eyes, so it looks a bit like a big satellite dish. It was one of the most powerful radio telescopes in the world, did all sorts of amazing science until one evening where in the middle of observing, it suddenly went from this to this. So I couldn't remember sitting at Subaru what had happened, but I was pretty sure someone had tried turning it off and on again. So I now had to make a decision. I really desperately needed the galaxies that I was studying that were billions of light years away for my thesis. If I canceled the observing run for a false alarm, I would forever lose the chance to get these observations. My PhD thesis might take longer to finish. I might not even be able to do the project I had set out to do. On the other hand, I was pretty sure that if I kept observing and the secondary fell off, I would be known as the grad student who broke Subaru and I would never get a job and this would just be a disaster either way. So now I was stuck trying to decide what my next move should be. This is actually the story that I used to start my book because it gives people a glimpse of the stakes and the feeling of sitting at one of the world's biggest telescopes, working as an astronomer and trying to decide what to do. I really love stories like this because they give us another perspective on space. It's really not hard to sell people on space as an idea. We all love these gorgeous pictures taken by a telescope like Subaru or like the Hubble Space Telescope, but we don't know nearly as much about the stories behind these pictures and the people who take them. I think if you asked somebody to describe or picture an astronomer, a professional astronomer in their minds, their picture would probably turn out something like this. They would probably picture a man with a beard in a space lab coat, standing next to a little telescope that you look through with your eyes. And it's a completely fair picture. This is how most of us have interacted with astronomy. You go to an event like this and get to look through telescopes at the sun with a proper filter. Or you might have a neighbor with a telescope in their backyard. This is how we all get introduced to astronomy, so you just imagine it done to a sort of extreme level. This was definitely the mental picture that I had of this when I was a little kid. So this is me at age 6. I'm very proudly sporting my Hubble Space Telescope t-shirt because it had launched earlier that year. And I already knew then that I loved space, I loved astronomy, and I wanted to be a scientist. But I didn't really know what that meant beyond science being fun. I don't think many 6-year-olds think about the nuts and bolts of their future job. I was mostly thinking about getting to explain the mysteries of black holes or talk to aliens or discover a new type of star. One of these has come true. But I never would have pictured what my job actually wound up being like. In my job, I've gotten to visit the tops of the most remote mountains on the planet. I get to literally play with space lasers, as you can see in one of the pictures. And I get to do awesome science along the way. So all of the adventures that I had, all the stories from my colleagues, all the incredible changes that astronomy's been going through in recent years, have all wound up shaping my book, The Last Stargazers. So this book takes you on a behind-the-scenes tour through all the adventures of professional astronomy. I really knew that I wanted to tell these stories to a big audience. I also thought people should hear them because there are some misconceptions about what being a scientist is like, and especially what being an astronomer is like. When I'm talking to people at a party, or when I tell someone sitting next to me on a plane, oh, I'm an astronomer, I can almost guarantee that I'll get asked one of 3 questions. They'll ask, do you have a telescope in your backyard? And then they get very confused when I tell them I live in Seattle. They ask, how are you even awake right now? I think they expect I should be permanently nocturnal. And they ask, have you ever discovered a star? Have you ever discovered something neat in the night sky? So these are all really understandable questions if, like most people, you don't know an astronomer or think all that much about what astronomers do every day. What I love about being asked these questions is that the answers to all three of them are actually way cooler than you might think. So I'm going to go through them one by one. And we'll start with, do you have a telescope in your backyard? Because again, when we picture professional astronomy, we tend to picture this. I was really lucky and I did have a little telescope in my backyard growing up. This is me and my dad getting to look through our little 8-inch telescope in the backyard. But this is no longer the tool that I use for my job. If you look at professional telescopes, you see places like this. We put these enormous building-sized telescopes, like the Subaru that you saw at the beginning of the talk, in very high, dry, remote places. We want to get to places that are incredibly dark. These are places like the tallest mountain in Hawaii or the foothills of the Andes in Chile. And the reason is that we want to get that beautiful, perfect, dark sky that we can use for our observations. When you get to a dark place like this, the sky is just exquisite. It's perfect for astronomy. You're out on this top of the mountain in the middle of nowhere, very far from light pollution, very far from other people. It can often feel like you're alone on the mountain. But you're not quite. You might be far away from a lot of people, but there's a few other things on the mountain hanging out with you. One of my favorite stories about this happened here at Apache Point Observatory. This is on the summit of a mountain in southern New Mexico. It's actually just a couple hours north of El Paso. It's high, it's remote, the sky is nice and dark. There really aren't any humans around. It's really common for the person running the big main telescope on the mountain to work an entire night and never see anyone. The weather is usually beautiful, so even when you're working on the telescope during the day, people will often prop open the windows or prop open the doors and let nature in. And on one day, somebody let a little too much nature in. They were in the middle of observing. They were working at a computer down the hall from the door. They stepped out the door of the computer room. They looked down the hallway and they came face to face with a fairly large bear that had wandered into the observatory. It might have had some astronomy questions. I don't know. Now, very luckily, the person looked at the bear and went, ah, and I think the bear looked back at them and went, ah, and they both ran, very luckily, in opposite directions and out opposite doors. But this was an example of the surprising encounters with wildlife we sometimes have in astronomy. Nature shows up at our observatories pretty regularly. We have local owls sitting on top of cameras that we point up at the sky. In Chile, we'll see things like guanacos, the wild version of llamas wandering around the observatory. Sometimes you run into Chilean tarantulas, which are very big and scary looking, but completely harmless as it turns out. We will often see Andean condors flying around the mountain. We will see creatures like viscachas. They're related to chinchillas. They look like wise little rabbit grandfathers. They particularly love hanging out at a lot of our observatories. So these are all really interesting creatures that we run into in our jobs. The most startling creature, though, is that especially here in the southern US, we will often run into ladybugs. Swarms of ladybugs will travel at certain times of year and alight on the mountaintops of telescopes. And when they do this, they get everywhere. They cover the domes, so it just looks like this teeming surface of red. They will climb into the mechanics of the domes and prevent them from moving. They will climb into cameras. They will climb into your dormitory. So people will regularly have observing runs that just get havoc wreaked on them by ladybugs. So if you remember the first trivia question that was posted, astronomers working at telescopes are often most scared of not bears or tarantulas, certainly not aliens, but ladybugs. So when we talk about nature intruding on our observations, we're not just talking about animals either. This is another observatory here in the US at Monastash Ridge in central Washington state. This is the observatory that my university, the University of Washington, uses for teaching and for a lot of student observations. And this observatory became the site for one of the most surprising nature intruding on our observation stories in astronomy. And this happened back in 1980. An astronomer named Doug Geisler was observing for his PhD thesis. There might be a little bit of a curse with observations like this. And he at the time was taking very careful notes about his observations in the observatory's night log. So you can see this page that walks through all the different details that you want to write about your night. How many hours you observed, how many hours were lost, the condition of the sky. He had a beautiful night of observations. He got great data. He wrote, oh, the night was clear. The sky condition was excellent. This was great. He went to bed in the morning as the sun was rising, and he marked the date as May 18th, 1980. And some people in the room might recognize that date. Because later that morning, he sort of half woke up, he heard this strange rumbling noise in the background, he kind of said, what was that? Went right back to sleep. He woke up around noon and opened the door of the dormitory where he was alone on the mountain thinking, I'll get blinded by the sunlight, I'll enjoy the beautiful midday heat and get ready for my observations. When he opened the door, he opened it into blackness. He couldn't see more than a few feet in front of his face. He grabbed a flashlight. That didn't help. There was this awful sort of sour brimstone smell in the air. And he went running back into the dormitory and started fiddling with the radio thinking, I'm living through the end of the world. What has happened? I'm alone on the mountain. What am I going to do? And he finally found a radio report explaining that earlier that morning, Mount St. Helens had erupted. Now, Mount St. Helens was a decent way from the observatory, but if you study the eruption of St. Helens, you'll notice that the side of the mountain basically blew off, and the volcanic plume from the eruption actually wound up blowing in a very specific direction. You can see it on a map. So, this was the volcanic explosion. Here's Doug. Yeah. So he was standing in the middle of the sort of fallout from this volcanic eruption. He was alarmed, but a little relieved that the world wasn't completely ending. He ran out to the telescope and covered it so that that corrosive volcanic ash wouldn't damage the mirror. And he then very carefully wrote about what happened in the night log like a good scientist. So, hours lost, 6. Reason, volcano, sky condition, black and smelly. Hours lost, 6, reason, volcano is now the title of the 4th chapter of my book, where we look at all these bizarre ways that nature can mess with and intrude with our observations. And this now gives you the answer to our second trivia question. So we do put telescopes in the middle of nowhere. We sometimes put them, I guess, a little too close to volcanoes. But telescopes have been sent to all sorts of incredible places in pursuit of our observations. Another question that got asked was where telescopes have observed from. The surface of the moon, the South Pole, the open door of a flying plane. It turns out the correct answer to this question is all of the above. We have put telescopes into some incredible places. We've carried them around the world to observe total solar eclipses. We've launched them on board balloons to send them high into Earth's atmosphere. We have an operating telescope at the South Pole. The picture on the lower right might puzzle a couple of you because I said early on, astronomy isn't guys in lab coats standing next to little telescopes. And it usually isn't, but this particular guy has an excuse. This is George Carruthers, and he is the inventor of the ultraviolet camera. He invented the technology that makes it possible for telescopes, like the Hubble Space Telescope, for example, to observe ultraviolet light. He is standing next to a little telescope that he built and designed that wound up traveling to the surface of the moon. It was flown to the moon on board Apollo 16. The astronauts used it for 3 nights to get some of our first ultraviolet pictures of the Milky Way, of our own planet. It was an incredibly long way to take a telescope, but we have already started the process of observing from places beyond even our own Earth. I think, though, that my favorite telescope on this slide is this one, which might not even be recognizable as a telescope at all. But this is the NASA Stratospheric Observatory for Infrared Astronomy, or SOFIA. This is a telescope built into the open back door of a specially modified 747. It flies up into the atmosphere well above most of the planet's water vapor to 45,000 feet, so it can observe light that would normally get blocked by clouds and water vapor and never make it down to the ground. I actually got the chance to fly on SOFIA for some of my research on dying stars and for some of my research for this book. We took off from southern New Zealand. We flew so close to Antarctica that we actually started seeing the southern lights out the window of the plane. I think flying on an experimental plane, observing dying stars, seeing the southern lights flickering out the window is the coolest thing I've ever done for my job. I tell this story in The Last Stargazers, and I think that is a pretty awesome answer to, do you have a telescope in your backyard? No, I get to ride in the open back door of a plane with one is a pretty fun answer instead. So now let's look at the second question on this list. How are you even awake right now? Shouldn't astronomers just work all night, every night to do their research? We definitely imagine astronomy happening at night. We picture an astronomer waiting by a telescope, looking at something like the moon. And we imagine somebody just peering patiently through an eyepiece, waiting for something to happen and taking notes. Very early on, this might have been what astronomy looked like, but astronomers quickly figured out that a much better use of our time was to go to a telescope pretty briefly, maybe just for a few nights, take pictures, and then go back to our day jobs and study those pictures. Taking the pictures is the real key here, because that's much easier said than done. This is a pretty nice looking picture of the moon. It's taken through a telescope, but the picture originally looked like this. The color was flipped, and it was originally taken in 1894. It was taken on something called a photographic plate. This is a very thin sheet of glass that's been specially chemically treated to darken when it's exposed to light. Astronomers would arrive at a telescope along with a shipment of photographic plates from a company like Kodak that had been chemically treated to get dark once they were exposed to light, which meant you had to keep the plates in the dark until you were ready to use them. Astronomers would slice them down to the perfect size to fit into a telescope's camera. They would do all sorts of tricks to these plates. They would sometimes bake them or freeze them. One person I talked to swore he would rub his plates with lemon juice to make them extra sensitive to light. And they would do all this, slicing the glass and treating the glass in the dark. They would then take these plates to a telescope's camera, climb into the telescope with the camera, slide these plates into and out of the camera, and spend all night with the telescope riding along with a night assistant helping them to turn the entire telescope so that they could take pictures one by one. Sitting in a telescope, by the way, sometimes means sitting pretty high. You would be up near where we saw that secondary mirror before at the beginning of the talk. Sitting next to the telescope, sitting next to the camera, having an assistant help you turn this telescope while you sat there, and whiling away an entire, sometimes very cold night, loading in glass plates one by one. You would sometimes have to expose one glass plate to the sky for hours. You could point it at a very faint galaxy, open the camera's shutter, and point the plate at that galaxy, waiting for it to slowly darken as the light from the galaxy hit it. Sometimes you would spend an entire night doing this. Sometimes you would spend several nights doing this. You would close the shutter, go to bed, come back the next night, point back to the same galaxy, open the shutter, and start again. So an enormous amount of work would get poured into these plates. You generally got exquisite pictures, though, of these faint, tiny galaxies, provided nothing went wrong. So this is an observatory in California, Lick Observatory. On the lower right in the front, you can see the biggest telescope on the mountain. And you can see the telescope towering into the air inside the dome if you look through the slit. There was an astronomer observing at this telescope, exposing a photographic plate that he had poured hours and hours of observations into. His night assistant had been helping him do this work. He would walk out to the dome, climb up a ladder, climb into the top of the telescope, and then sail away from the ladder as the assistant turned the telescope. This was going great until the assistant stepped into the dome to check on how his astronomer was doing. And as he stepped through the door, his jacket sleeve caught the light switch on the wall of the telescope. Yeah. So this light goes pouring into the telescope. It floods the plate. It ruins it. And the astronomer just lets out this howl from up at the top of the telescope and starts yelling, "How dare you? You've ruined a night of hard work. I'm going to get down from this telescope and kill you." And he then starts trying to turn the telescope very slowly, turning it slowly toward the ladder sitting on the wall so that he could climb down and make good on his threats. And the assistant was looking at him going, "He seems really mad. I don't think I should let him down until he's a little less angry." So the assistant started turning the dome that the ladder was attached to. So the ladder's speeding away, the astronomer's going after it, he's yelling, the assistant's going, "I'm not letting you down until you get less angry." And somebody else on the mountain would have looked over and seen this giant telescope with the lights blazing and the dome just doing this. So it would have been pretty ridiculous. And the whole idea of using photographic plates seems ridiculous. These plates are really primitive sounding. You have a sheet of glass, you chemically treat it, you wait for hours to get data. Did we really do astronomy this way? We did. We actually made some astonishing discoveries using photographic plates. I showed you this picture earlier of an astronomer sitting at the main camera of an enormous telescope, but I didn't tell you who this astronomer is. That is Edwin Hubble. And one of the trivia questions asked you what Hubble was famous for. A lot of us know the Hubble Space Telescope that's been named for him, but it's a little less common to know why Hubble got a telescope named after him and what he is so famous for. Edwin Hubble, as it turns out, discovered is famous for discovering the expansion of the universe. And he did this using glass plates. This is a plate observed for Hubble's research of the Andromeda Nebula, as it was known when he first looked at it in the early 1920s. Now, he took this plate, he then carried it back to his day job work, and when analyzing it afterward, you see he wrote this word VAR on the upper right-hand corner of the plate. That VAR is short for variable star. He had found a star in the Andromeda Nebula whose brightness was varying very regularly. And he knew he could actually use that star and its variations to measure how far away the Andromeda Nebula was. This was interesting because there was a really fierce debate going on at the time in astronomy about what Andromeda was. Was it this weird spiral-shaped blob of stars inside our Milky Way, or was it an entire separate galaxy way beyond our own Milky Way? It was mind-blowing to people at the time to imagine that there could be other galaxies, that the universe could actually be that big. When Hubble measured the distance to the Andromeda Nebula, though, that's exactly what he found. He found that this was the Andromeda Galaxy. We know today that this galaxy is 2.5 million light years away, and it's actually one of our Milky Way's closest next-door neighbors. Hubble's discovery, though, blew open our entire perception of how big the universe was. He went on to study heaps of other galaxies, and he used their motion to explain that the universe was expanding. But he did all of this using those little sheets of glass. Today, our telescopes have digital cameras on them. They're not too terribly different than the kind of cameras we all have in our phones. But the fact still remains that most of the science that we do is based on those pictures. We go to the telescopes briefly at night, take the pictures, and then do most of the research while we are awake. So this is how I and many other astronomers, including the folks you met here today, are awake right now. We don't have to stay up all night every night to do our research. So another cool question and another cool answer is, have you ever discovered a star? The cool answer, I think, here is that we've actually moved way beyond discovering stars in astronomy. If we go back to our cartoon picture of an astronomer, and if you look up stock photos of astronomers, you see pictures like this. There's a lab coat, there's space safety goggles, apparently, and he's pointing, going, look, it's space. I've discovered space. And this is how you imagine a lot of astronomy working. You maybe wait at a telescope, look at data, and then you say, oh, look, it's a new star, I found one. This almost never happens. I say almost on purpose, and I will explain that in a minute. But for the most part, we now have a very encyclopedic knowledge of the stars that are in the sky. We have immense catalogs that list what's in the sky. This is data from the European Space Agency's Gaia satellite. It has measured with amazing precision the positions of 1.8 billion with a B stars in and close to the Milky Way, and 1.6 million background galaxies. So we don't need to find the billions of stars that Gaia has observed. It's now less about finding things and more about explaining things. Really often in astronomy, if we spot something new or weird, the challenge is to take what we know about the universe to try and explain the strange new thing we're studying. And one of the strangest detections that's happened in astronomy in the past couple decades actually happened at Parkes Observatory in Australia. So I showed a telescope that looked like this before. This is a radio telescope. I'm sure some of you saw demos about this today, but to very briefly explain, when we talk about light, we talk about the full electromagnetic spectrum. So all the light that gets emitted by things, including the light that we can see with our eyes. We can see visible light, but if that light got a little bluer, we'd be talking about ultraviolet light, probably the reason hopefully everyone wore sunscreen today to come to the physics festival. If the light turns a little redder, we get into infrared light. You might have seen a demo here at the physics festival showing what you look like in infrared light thanks to a special camera. Now, if we keep going and make light redder and redder and redder, you wind up with radio light. And to study this light, you need slightly differently designed telescopes. Instead of a nice shiny looking mirror, you wind up with this big bowl of a satellite dish. Parkes Observatory was observing radio light one night in 2007 when it suddenly picked up this weird brief flash of radio light. And it caught everyone by surprise. This wasn't something that had been predicted or expected. There was this brief burst of radio emission, and then it went away, and everyone went, wow, that was very strange. We don't know what that was. And it was marked as a footnote and as a strange thing that people wanted to study. Several years later, a young woman named Emily Petroff showed up at Parkes Observatory to do her PhD thesis. And she said, well, I want to study bursts like that. I want to study these weird objects that you've been finding. I think they could be really scientifically interesting. And the answer was, no, you probably don't want to study that. We've actually been detecting a ton of these things, and we're pretty sure they're not real. We're pretty sure this is not actually a radio signal from space. We're pretty sure this is radio interference from something here on the ground. If I could snap my fingers right now and let all of you see in radio light, the room around us would look really different. You would see the hum of the university Wi-Fi. If you looked out toward the road, you might see the little flashes of spark plugs in car engines as they drove by. You would not necessarily see the same light that you're seeing now, but you would see all the things that emit radio light here on the ground. If you can see those things, then radio telescopes can see those things. And the crew of this observatory was convinced that all these weird little bursts were some strange signal from something on the ground messing with the telescope. They'd actually nicknamed these events peritons, which is a mythical creature that looks like one thing, but it casts the shadow of something else. Emily was not convinced that there was nothing to these signals. She thought there might be some real science buried in there. But in order to do that, she first had to help explain what these peritons actually were. The folks at the observatory still regarded it as a mystery. So she wound up rounding up the entire staff of the observatory to work on solving this problem and to figure out what strange thing here on Earth was causing peritons. And the first clue that gave them an idea was noticing that when the peritons were detected, they tended to happen around lunchtime. So space is weird. Space does not care, though, what time lunch is in Australia. And this was their first hint. If you look at this aerial picture of the observatory, you can see 3 arrows pointing to 3 outbuildings at the observatory. And those 3 buildings all have administrative offices. They all have break rooms. All those break rooms have microwaves where people can heat up leftovers or a snack. And these were immediately seen as potential culprits for peritons. The people doing this research were such good, careful scientists. They did this test so carefully. They described running the microwaves on low and high. They always microwaved a ceramic mug of water. They would run a microwave and then check the telescope. And it wasn't working. The telescope wasn't detecting anything. The microwaves were running. They were fine. The telescope was silent. There didn't seem to be a problem. And then someone finally realized we're being too good at science right now. We're being very careful about this. We're not acting like hungry people microwaving our dinner. Because when you microwave something and you're waiting for the popcorn to be done, you're waiting for your dinner, you don't wait for the microwave to finish. You know you don't. You watch it count down and it's going 3, 2, close enough. And you open the door to stop the microwave and get out your food. When they did this, when they ran the microwaves but stopped them by opening the doors before their sequence had quite completed, they did it. They produced a periton and they were able to see that signature at the telescopes. So, another trivia question. Australian astronomers successfully discovered microwave ovens starting in 2007. So, they went back to the drawing board and they said, all right, we can probably explain all of these signals. There's probably nothing to it. But Emily was still working on this and said, let's go through and make sure that this really is the explanation. And they got rid of all of the peritons except the first one. That strange event from 2007 that got them keeping an eye out for these weird flashes in the first place was real. That had not been produced by a microwave. That turned out to be something that we now call a fast radio burst. And astronomers are still studying these things today. We still don't quite know what they are. We think they have something to do with dying stars. The mystery is ongoing, but we never would have even started studying them if we hadn't first ruled out inpatient microwaves. So these are just one example of the weird sources of interference that can mess with things at telescopes. I think my favorite story about these actually happened at Green Bank Observatory in West Virginia. So you'll notice the big, beautiful new radio telescope at Green Bank that has replaced the one that we saw collapse at the beginning of the talk. They rebuilt a telescope in this exact place because this part of West Virginia is actually one of the best places for radio astronomy on the planet. It's in the middle of what's known as the National Radio Quiet Zone, and they go to great lengths to prevent things like that microwave interference or anything else emitting radio light that could mess with the telescopes trying to detect very faint radio signals from the universe. As you get close to this observatory, if people have microwaves, they're kept in a special blocked container. You don't have Wi-Fi, you don't have cell phones. The cars that drive to this observatory actually run on diesel because those little flashes from spark plugs would be too much. They go to such enormous efforts to keep this place as free of radio interference as possible, and it almost always works. You can see that it's in the middle of this lovely, beautiful natural forest, and not too long ago, some researchers working in this state forest decided that they wanted to study the forest's population of flying squirrels. They wanted to study how these squirrels moved, how they behaved. It was an excellent biology research project. But to do this, they had to catch all the squirrels, and to track their motions, they had to fit them all with little radio collars. So they then unleashed this adorable swarm of radio interference sources into the trees around the observatory. And apparently for weeks, they could not observe because they would try to point at the massive black hole at the center of the galaxy and they would just get squirrels. Or they would try to study one of these weird bursts that we couldn't explain and just squirrels. And everything they did, they just kept picking up squirrels. They eventually did engineering work and they waited for the batteries and the little collars to die. And that was the only way they could get back to observing. Because you're not going to catch a flock of flying squirrels at this point in the project. So this now explains another one of our trivia questions, that the largest radio telescope in the continental US once closed due to, yes, flying squirrels. So sometimes we're just spotting weird phenomena and looking for explanations. At other times, our discoveries in astronomy actually come not from finding a new thing, but from looking at an old thing a bit more closely. So in the middle of this image is one star that actually represents a totally new model for how we think stars can work. Now, most stars are basically running little nuclear fusion reactors in their cores. They're fusing hydrogen into helium or helium into carbon. That fusion is producing energy that helps the star sort of fight the inward crush of its own gravity. You get this very delicate little balancing act of fusion generating energy and gravity crushing the star inward, and this works right up until the star dies. But this particular star is working slightly differently. Its core is actually coming from a star that has already died, a star whose core has collapsed and produced this strange leftover dead husk of a star known as a neutron star. These stars aren't supported by fusion, they're supported by weird principles of quantum physics. And we know that this star represents that weird new model because we took a very close look at it and studied its chemistry. Thanks to that chemistry, we can now back up and build a story of how this star formed. We think that this star used to be two stars, sitting in a binary, orbiting one another. The larger of those two blue stars reached the end of its life, and then one day that balancing act ended and it collapsed as a supernova. You see the bouncing off, rebound shock of a supernova spraying out into space. Some of you might have seen that demo at Physics Fest. It's left over, that little leftover dead neutron star that then gets swallowed by the companion as it expands into a big red star known as a red supergiant. This new weird type of star is something known as a Thorne-Zhitkov object. From the outside, it looks like a red supergiant, but it's got this dead star as its core. This is actually the research that I got to lead when I wound up fulfilling one of my little childhood fantasies of I want to discover a new type of star. This is what discovering a new type of star looks like. It's not finding the star with the arrow pointed at it. It's taking a really close look at it to discover what makes it so unbelievably weird and exciting. So this need to look very closely at stars and to really get a detailed look at how things work is a huge part of why we keep building and designing new telescopes in astronomy. This is a picture of the James Webb Space Telescope, which was launched just a little over a year ago. It is 6 times larger than Hubble. It's 100 times more powerful than Hubble. It's now observing 1 million miles from our planet. This is unbelievably exciting, not just because of how incredibly far it can see, not just because of its increased size and power, but because it's a new way for us to see the universe. We're looking at a different light. Again, I showed you the picture of the electromagnetic spectrum earlier, and some of you probably saw this demo during the Physics Festival today. This is a galaxy nearby that we have a beautiful picture of from Hubble using visible light, the light that we all see with our eyes. Now you can watch how this same galaxy looks if instead of looking at it with visible light, we switch to observing it with infrared light. You can see how much it changes. I'll back up and do that same change again. You can see that different parts of the galaxy are bright or dim. We can see and study the dust in the galaxy a little bit more. Even the background galaxies in this picture look different. By looking at the universe with a slightly different type of light, we get to see incredible new different things, and we get to answer long-standing questions that we haven't been able to fully tackle with the telescopes that came before James Webb. So this means we can study all sorts of incredible things with James Webb. This was another trivia question that you might have seen. We can study the first generation of galaxies in the entire universe. We can get a really interesting glimpse at new stars being born. I know aliens looks like a joke answer on this plot, but the real answer is all of the above. James Webb is even going to be capable of searching for other planets and signs of life on other planets. So, even observing planets around other stars and looking for life on them is a thing that James Webb is going to be able to do. This is actually a subfield of astronomy called astrobiology. It sounds like science fiction, but it's a real and serious research area that scientists are working in today. So I said earlier that we almost never discover brand new stars in the night sky. We almost never see a new star appear and get excited over what it's doing. There is one exception, and this exception occurred in 1987 and was observed by a man named Oscar de Halde. He was a Chilean engineer working at one of the telescopes in Chile at Las Campanas Observatory. If his name seems a little familiar to you, this is why. You saw him on a trivia slide. He was the last person to discover a supernova with the naked eye. Oscar had worked at these telescopes in Chile for years. He knew the night sky incredibly well, and he was particularly familiar with this little piece of the sky. This is the Large Magellanic Cloud. It's a little galaxy not too far from our own Milky Way. It's a satellite galaxy of our Milky Way. Oscar had worked on it for years, and he knew every detail of where every little star and where every little sort of scrap of light was coming from in this galaxy. One night during observing, he stepped outside, he had his coffee, he was taking a quick break. He looked up at the night sky and he immediately went, oh, that galaxy looks different, something's changed, because it looked like this. It looks the same to almost everyone in the room, right? A new star had appeared in that galaxy, and because Oscar knew the galaxy so well, he was able to recognize it. I'm going to back up and show it to you again, and I'm going to see if you can see the star. See, everyone notices when it disappears, but bing. So that was the new star that Oscar had noticed. Here, I'll point to it so that everybody can get a good look at it. This looks like a new star. It's actually the pinprick light of a new supernova that happened in this galaxy about 200,000 light years away. It doesn't look too dramatic. You don't look at it and think, wow, that's definitely an exploding star, but you have to remember how incredibly far away this is. The fact that Oscar was able to notice this change and see this, and the flurry of research that this kicked off as heaps of astronomers raced to study this new supernova in 1987, is one of the only examples of somebody actually saying, I've discovered a new star and it's about to get really cool. So these three questions, I think we can agree that all the answers to them are pretty cool. But there's a fourth one that I've been starting to get asked more and more these days as I tell somebody I'm an astronomer and that I travel to these telescopes and do this sort of research trying to understand the universe. People will ask, can't computers do all of this now? Aren't we starting to teach computers things such that they can take over a lot of the research? And they're not wrong. The power of computer science and astronomy is amazing. I showed you this observatory with the visiting bear. Telescopes like this one can now be operated remotely. I've run this telescope from Colorado, from New York City. I've run it from Switzerland. You can be anywhere in the world, open up your laptop with the right software on it, and log in to observe remotely with a telescope like this. And this has been happening with more and more telescopes all over the planet. The photographic plates that I described that you would sort of labor over and put into a telescope camera one by one have gone by the wayside for several decades now. We now have digital imaging, and you can see how a photographic image of something like this beautiful little galaxy taken on a photographic plate can turn into an exquisite digital image, taken in this case with Subaru, the telescope that I was sitting at the very beginning of the talk. And now, we can even automate things like what Oscar did. This idea of spotting a brand new star, bing, as it observes. With a lot of effort and careful work, we can now teach a computer to do what Oscar did with his mind and discover these newly appearing stars or discover things that change in the night sky. There is a brand new telescope getting built. It's going to start collecting light in about another year or so. And it's named after Vera Rubin, the woman who discovered dark matter. It's in Chile, and its job is going to be to just take pictures of a huge swath of the southern sky over and over and over again for a decade. Those pictures are going to pretty much give us a decade-long movie of the night sky. So we'll be able to see every little thing that changes. We'll be able to see that little pinprick of a new supernova appearing. We might see stars that just disappear because they collapse into black holes and vanish. We'll see things like asteroids scooting through the night sky, maybe even asteroids that are coming a little bit close to Earth. So Rubin is going to be capable of discovering all sorts of strange, changing things in the night sky. Computers are going to do incredible things for astronomy. They already have, and there's no reason to think this won't continue. But there is one thing that computers really can't do, and I'm going to have you demonstrate it. So what things are you still curious about the universe? What strange objects or strange mysteries or strange phenomena do you still want to ask questions about? I heard aliens. More aliens. Yell it out, black holes. Thorne-Zhidkov objects. I agree. Supernovas, all sorts of things. Excellent, yes. That, what you are doing right now is what computers cannot do. Computers can help us answer these questions, but they can't ask them for us. They can't have these really creative ideas and these really curious questions about how the universe works and how we want to study it. A computer isn't going to ask, what's out there? Where do we come from? I heard someone say, what's inside a black hole? And they definitely don't immediately ask, what about aliens? So I've been keeping aliens on these slides the whole talk. This is not just an April Fool's joke. This is one of my favorite examples of very creative astronomy, and we've been studying aliens as humans for a lot longer than you might think. Back in August of 1924, Mars was getting ready to make its closest approach to Earth in more than a century. Earth's and Mars's orbits were taking them surprisingly close together. In the early 1900s, astronomers already saw radio as a potential way to pick up signals from something like extraterrestrial intelligence. So ahead of this close pass with Mars, they wound up hatching a plan. They advertised this National Radio Silence Day for a 36-hour stretch around August 21st to 23rd. Civilians were all asked to be radio silent for 5 minutes, not run the radios in their homes, not produce any radio signals, to be silent for 5 minutes every hour on the hour. While they were doing this, naval stations around the country were listening for what they described as electrical phenomenon of unusual character, so aliens. Supposedly, some folks from the US Naval Observatory actually launched a dirigible into the lower atmosphere carrying a radio receiver to try and listen for Martians. The people doing this even had a cryptographer on staff who was ready to translate any alien messages that might have come in. It sounds ridiculous, and it's true that they didn't detect aliens, but if you look, they've invented radio astronomy, they've invented airborne astronomy, and they've invented astrobiology all in one go. All of this is research that we are still doing today, and it came from somebody having this wacky idea of what if we just made everybody be quiet on the radio and listen for aliens? So this is not something that a computer would come up with and do. There's one last story that really shows us the power and the promise of human curiosity, and it's the last trivia question that I asked. The Hubble Space Telescope made history in 1995 when for 10 days it observed not aliens, not an exploding star, not the rings of Neptune. Hubble pointed at nothing. This was an idea posed by Bob Williams, the director of the institute that runs Hubble. Shortly after Hubble was launched, they already knew what an incredibly powerful telescope it was, and they knew that it could see far deeper into space than we could see with our eyes, and far deeper than other telescopes had accomplished. He got the idea to point at a tiny, seemingly empty patch of sky and just let Hubble observe for dozens and dozens of hours, staring at this faint patch of sky to see what might be there in a place that looks empty to us but doesn't look empty to a powerful telescope like Hubble. When he did this, this is what came back. This is a picture known as the Hubble Deep Field. We went on and did this several more times with Hubble, but even in this first picture, we saw about 3,000 distant galaxies, all sitting in that tiny patch of seemingly dark sky. The most distant galaxies in this picture are 10 billion light years away. We know how fast light travels. So if something is 10 billion light years away and the light coming from it is coming to us at the speed of light, we are seeing it as it looked 10 billion years ago. We're using Hubble as a time machine, pretty much. We're looking back in time and seeing what galaxies looked like at a far earlier point in our universe. So this was an amazing thing to do with Hubble. We've now done something really similar with James Webb. This is a new Webb observation, also pointed at a seemingly dark, tiny patch of sky. Now we knew that there were galaxies there, but we wanted to see just how deep Webb would be able to observe. Just for scale, too, this area of sky is about as big as a grain of sand would be if you held it between your fingers and put it out at arm's length. Even in that teeny tiny patch of sky, there are still more thousands of galaxies. And the most distant ones that we see here, the little tiny red smudges that you can barely spot in the background, are more than 13 billion light years away. So this picture from Webb and that picture from Hubble and this beautiful discovery that came out of, hey, let's point a telescope at nothing, is another example of the amazing human creativity that is important in science and why I think that matters so much. So this is the thought that I want to leave all of you with. What other big questions do we have? The questions that you were shouting out. What questions of those do we need to answer next? What other unpredictable or surprising things are just waiting for us to ask the right questions? Whatever dark matter. This is great. This is just going to keep happening the rest of the time. So whatever these questions are, we need you. We need humans. We need stargazers to ask them. And we need the tools of astronomy and the adventures of astronomy to help us answer them. So thank you all very much. I do indeed have time for some questions. Mm-hmm.
I'm sure, well, maybe they're questions.
And don't go anywhere at the end because I've been told there are t-shirts happening too. So I see some hands up, so I think there are some questions. You, yeah. Okay. How about you? Her. And then you. Yep. What have astronomers figured out about the Big Bang? Oh, cool. So these sorts of pictures where we look very far back into the universe, where we're sort of looking back in time, help us look at what the universe was like shortly after the Big Bang. This snapshot is less than 1 billion years after the Big Bang. I know that doesn't sound like a short amount of time, but when you're talking about a 13.7 billion year old universe, that's pretty good. We're starting to figure out why the Big Bang happened, how the Big Bang is going to affect what's happening to our universe from here. Somebody like Nick is an expert on this sort of thing, so we're still figuring this out, but we're learning with the help of telescopes like Webb and pictures like this. Yeah.
So can you make a telescope bigger than the Hubble, and so then you can see what the Big Bang actually is?
We hope so. We are making telescopes bigger and bigger. Webb is bigger than Hubble, and there are other telescopes coming that are even bigger than that. We're also making telescopes that can see all sorts of different light, because sometimes to study that part of the universe, you want to study light that you can't see with our eyes. We're building new telescopes like this all the time to help try and answer this question. Yes? The oldest star in the universe that's recorded so far is about as old as the universe is. It's well over 13 billion years old. We can study stars like that right here in our own Milky Way. We look at their chemistry and they have this sort of snapshot chemistry of what the universe was like an incredibly long time ago. So almost as old as the universe are the oldest stars. You have to wait for the very first stars to sort of be born and condense out of the gas and dust that was left in that was there in the very early universe. But yeah, they're super old. Other questions? I saw a hand on this side of the room. Yeah.
What happened in Hawaii? What was your decision in Hawaii?
What happened in Hawaii? What happened to that telescope that needed to be turned off and on again? I know my answer should be, well, you'll have to read the book, but it's fine. The telescope's fine. The telescope made it. I still have a job. We turned it off and on again, and it wound up working. So, question from this side of the room I thought I saw. Yeah. Can I make the picture any bigger? Sadly, not now. If you go online, though, if you go to NASA's website and you look up pictures from the James Webb Space Telescope, you can get this picture on your computer and you can make it huge and you can zoom in on it as much as you want. So you can take a really close look at it just by going to their website. Other questions? Oh no. So I got asked the question, what exactly is dark matter? That is an excellent question. This is a great example of one of the questions that we need people to answer. We still don't know. Now we know that dark matter is matter that has some sort of weird mass. I actually think the name dark matter is a little funny because it makes it sound like you're looking at these weird dark blobs in the universe. But dark matter isn't really dark. It's not really bright. It's not really anything. It doesn't interact with light at all. But we do know that it has mass. It has gravity. I know that we'd had some demonstrations on gravity at Physics Festival today. And we can see what dark matter's gravity does to things around it, like stars, like galaxies. We just don't know what it's made of yet, and people are still trying to find out. This was what Vera Rubin discovered, and her discovery actually started a whole little field of physics where people are trying to figure out if dark matter is some weird sort of particle or some sort of astronomical object we don't fully understand yet. So we still don't know. We need people to keep asking, what exactly is dark matter? Yes? Sorry? You, yep. Great question. Do I think dark matter was made out of a collapsing dark hole or a collapsing black hole? This was one of the ideas that astronomers had, professional astronomers early on. They said, well, that sounds perfect. That could be a great explanation for what dark matter is. We don't think it is anymore because something like a black hole does interact with light in very funky, weird ways, and dark matter doesn't appear to interact with light at all. So it's an excellent hypothesis that astronomers had, but they tested it. It wound up being wrong, so they're still trying to come up with other ideas. Other questions? Yeah? What have we learned from the James Webb images? Well, just from this one, we've gotten to see galaxies even further back in time, even closer to the beginning of the universe than we ever have before. This is one really beautiful camera on that telescope. We have other cameras that can do things like measure the chemistry of galaxies. So we've now measured exactly how much, say, hydrogen or oxygen or nitrogen is in these galaxies that are incredibly far away. Those sorts of observations would have been impossible before we pointed this telescope at those galaxies. So we're starting to learn a lot about what they're made of. We're starting to look at other planets and getting really close looks at other planets to see if there might be signs of life. James Webb has only been observing for about a little over six or 9 months or so. So we're still very early in finding out what we're going to learn from it and what we're going to discover about it. So you'll probably see a lot of cool stuff in the news about what they're discovering in the years to come. Mm-hmm. How will we ever figure out what's inside a black hole? That's a good question. What I like about that is it's a question about a question. It's saying, how can we answer that question? How can we decide what's in a black hole? This is pretty hard because black holes do very strange things to light. They do very strange things to space and to time. It might be impossible to peer directly into a black hole and learn exactly what's going on inside it. But this is where a lot of the physics that you all learned about today comes in handy. Because even though black holes can be very difficult to observe, we can use the predictions of physics and the theories of physics and the math of physics to say, based on what we see, this is what must be happening inside a black hole. For a black hole to work the way it does, this must be what's happening inside it. So it's a little more complicated than just pointing a telescope at it, but if you take that and combine it with all the physics that you heard about today, that's how we're going to start getting an answer to that question. I saw questions over here. Yes? What's the largest telescope used? So there is a radio telescope in China right now that is built. It doesn't quite turn. It actually just sits in the ground and has a big receiver on top of it that can move back and forth to help it point at different parts of the sky. It is over 1,000 feet from end to end. I know. And that's the biggest telescope that's currently operating right now. We used to have a telescope almost that huge in Puerto Rico that did the same number of same types of observations. This is called the Arecibo telescope. And Arecibo, very tragically, underwent a collapse, not too different than the picture that I showed of the Green Bank telescope a couple of years ago. We're really hoping, though, that we can rebuild something there or do something to make up for the loss of that telescope, because it was an amazing one. But that's how big the biggest telescopes are right now. Yes. Yep. Mm-hmm. Do people still ask about aliens? Oh yeah, I work with people whose entire job is asking about aliens. Their entire career is astrobiology, which, like I said, it sounds like science fiction, it sounds pretend. But their entire work is trying to figure out, if there were aliens on another planet, what would that planet look like? What would it look like if aliens were trying to talk to us? What would it look like if there were dinosaurs on another planet? If there was an entire planet just covered with moss or mushrooms or trees? They really try to figure out all the different ways that you could possibly see life on other planets. So this is people's full-time job, asking about aliens. Other questions? Yep. Yes. Mm-hmm. Yep. Mm-hmm. Go ahead. Yeah. What's the biggest galaxy ever discovered? That's an awesome question, and I don't know the answer. I know people do. I have colleagues who study galaxies and study how galaxies actually form and how galaxies evolve. Believe it or not, as you sort of build a galaxy and watch it change over billions and billions of years, they change very much. They would know what the biggest galaxy ever studied is. I don't know the answer, and I don't want to try and guess, because it's always hard to guess when numbers get this big and this wild. So I would suggest looking it up, and let me know, because now I'm curious. Other questions? Yeah.
So, is there any other kind of weird star combos, like Thorne-Zitkov objects?
Are there any other weird type of star combos like Thorne-Zitkov objects? We think so. We think that there are stars that have sort of the leftover blobs of something like our sun when it dies in their centers. We even think that there could maybe be stars that have black holes at their centers. I know. Yeah.
What's the video about that?
Mm-hmm. That you can find videos and stories about a lot of these things if you look very carefully at scientists talking about this online. It's always important to look at who is talking to you about this, because you want to hear from scientists who have studied these things and who know what maybe was a cool idea that didn't work out and what's a cool idea that we're still studying. But we are still trying to study other weird combo stars like that.
Yeah, I'm this really weird guy who kept doing stuff, and I was like, okay, it was good for a few years, and then it was like, no, I want to start saying false stuff.
Oh, that's never good. Nope, you want to listen to people. You want to listen to people who are very good and skeptical and being very careful with the science that they talk about. All right, how about you?
What happened to the baby's telescope? How did it break?
What happened to that big telescope? How did it break? So the reason that telescope collapsed was that the people who built it were really, really careful. The engineers who designed it were super careful, but they built one little piece of the telescope that was very important and had to hold up a lot of its weight. And that piece of the telescope was just a little bit smaller than it was supposed to be. And the difference was so small that for a long time, nobody even noticed there was a problem. But one day, just because that piece of the telescope was a little too small, it started to fail. It was getting squished under too much weight, and it started to collapse, and then the whole telescope came down on top of it. Very luckily, nobody got hurt when something like that happened, but it meant that when they went back and rebuilt the telescope, they had to be pretty careful to measure everything exactly right. Do we have time for more questions, or should we?
If you can.
Yep, definitely. Yes.
What's your idea about multiple big bangs? Like, everybody's talking about metaverse in movies these days.
Oh yeah, what's the idea about multiple big bangs or the metaverse? So these are actually sometimes two different questions. Multiple big bangs is pretty difficult to study, and I'm definitely not the expert to ask about things like that. Something like the metaverse, which I think we've seen in like a bunch of different movies right now. This is a very popular movie question. This is a theory that actually ties into how we think the universe was made, how we think the universe forms, how we think the universe evolves. Again, it sounds like science fiction, but there are scientists studying this. It's not what I study, so I don't have a good answer for you saying, well, I think it's this, because I would need to go listen to those colleagues and hear the questions that they're asking and the answers that they're getting. But people really are seriously studying things like parallel universes or multiple universes, whether they could exist, and what I think is most important, how we can ask good questions to prove that they exist or don't exist, how we can tell if something like that is really happening.
Get two more questions.
Two more questions. Hi.
Alright, okay.
Mm-hmm.
Do you travel a lot with it, or like did you do it at the beginning and then you slow down with computer development, or like what's your travel, like where you're staying?
This is an awesome question. Do I travel a lot for my job? So I do, and this took me totally by surprise because I really didn't travel when I was growing up. I didn't take many plane trips. My family didn't go all over the world or anything like that. I thought it sounded cool, but it wasn't something that I got to do. And then when I got to college and started doing astronomy research, I started traveling to Chile and to Arizona and to Hawaii and to all sorts of incredible places for conferences or to meet with other scientists. I'm actually here right now, fresh off an airplane from New Zealand, because I'm doing research in New Zealand right now during part of a research break year that I'm taking from my job in Seattle. So I'm traveling a little bit less as we've gotten better at automating telescopes. I actually haven't been to a telescope on the top of a mountain since before the pandemic, and I badly miss it because these are some of the most beautiful places on the planet and they're great places to work. But you do a lot of traveling for this job. And I did not expect that as part of studying astronomy, I was going to be discovering my own planet. But it's been really awesome to get to do that much travel. And then one more question. Yes. Oh, right here. Yep. Go ahead. Are there still planets that we haven't discovered? This is a great question. We have discovered thousands of planets at this point. A few decades ago, we were discovering the very first couple planets around another star, and they not caught us by surprise, but it was very exciting when we found 1 or 2 or 3 planets around other stars. Now, thanks to new telescopes, we've discovered thousands. We've discovered a teeny tiny micro number of the number of planets that exist. So we still haven't discovered pretty much all of the planets that we could see. And there are astronomers who are still very carefully looking, not just for planets that can have aliens on them, but for planets, period. So we have tons and tons of planets still to discover, and we're building new ways to do that all the time. And we're going to need people to keep asking questions like that so we can keep finding more of them.